गुड मॉर्निंग।
मॉर्निंग में
भार्गवी मैम ज्वाइन कर लिए क्या?
ज्वाइन हुई थी मैम, अभी अभी लेफ्ट हुई है, शायद वापस ज्वाइन नहीं, ज्वाइन है मैडम, ज्वाइन है।
ठीक है।
हेलो, नमस्कार।
नमस्ते।
नमस्ते मैडम।
हिरवानी सर बतलाइए, मेरी एम आई ऑडिबल?
जी जी मैम, आपकी आवाज आ रही है।
ओके, ठीक है। Bhargavi ma'am, how can we check how many of them have joined through YouTube link?
प्लीज पार्डन।
हेलो।
हाँ हाँ मैडम, बोलिए ना।
YouTube लिंक से जो ज्वाइन किए हैं उनका फिगर कोई बतलाएगा क्या?
हाँ, वो लिंक पे जाके चेक कर सकते हैं। वैसे मैं एक बार
किसी
चेक
को
कर
नहीं, नहीं
मैं
आप
देख
मत
लेता
करो,
हूँ मैम,
हाँ
मैं
किसी
देख
और को
लेता
बोलो।
हूँ।
हाँ, आप अपना
मैं देख
फोकस
लेता
करो
हूँ।
इस पे। हाँ। भुवनेश्वर वर्मा सर, जैसे ही वहाँ रेडी हो जाते हैं साइंस कॉलेज में, तो आप प्लीज बताएंगे।
वर्मा सर शायद ज्वाइन नहीं हुए ना।
अच्छा, तो मैं कनेक्ट करती हूँ। स्क्रीनशॉट के लिए इरवानी सर आप ले सकते हैं स्क्रीनशॉट ड्यूरिंग द प्रोग्राम।
यस मैम,
हाँ
मैं ले लूँ।
ठीक है, ओके। और लेखराम आप थोड़ा वर्मा सर को फोन लगा के उनसे पूछिए, जैसे ही सर
जी,
वहाँ
जी।
रेडी होते हैं वी विल स्टार्ट द प्रोग्राम।
जी जी।
ठीक।
मैम यूट्यूब पे मैं अभी ज्वाइन होना स्टार्ट नहीं हुआ है मैम।
Arbaz, have you joined? Arbaz Sheikh from MSc Physics, Science College.
शायद नहीं है।
यस मैम।
हाँ, Arbaz, you can ask your classmates to join through YouTube as I instructed. सुबह मैंने मैसेज डाला था कि YouTube से अगर स्टूडेंट्स ज्वाइन करेंगे तो इस पे लोड कम पड़ेगा गूगल मीट पे, तो
यस मैम।
है ना, आस्क ऑल द स्टूडेंट्स टू ज्वाइन थ्रू YouTube लिंक ओनली।
ओके मैम।
हाँ ठीक।
गुड मॉर्निंग मैम।
गुड मॉर्निंग। यदु सर, आपके प्रिंसिपल ज्वाइन किए हैं क्या? प्लीज कंफर्म।
हाँ मैडम, अभी कर रहे हैं, बात हुई है जब ज्वाइन हो रहे हैं।
हमारे कॉलेज में भुवनेश्वर वर्मा सर बतलाएंगे जैसे ही सर ज्वाइन करते हैं, उनको मैसेज किया है मैंने।
वर्मा सर से बात हुई मैम, तो अभी
हाँ।
प्रिंसिपल सर आने वाले हैं, बता रहे हैं, वो चैम्बर में बैठे हैं, बता रहे हैं प्रिंसिपल
ठीक है,
चैम्बर में।
ठीक है, उनको ओके करने बोलना जैसे ही सर आते हैं तो, है
हाँ
ना?
वो अभी
हाँ।
ग्रुप में ज्वाइन कर रहे हैं मैम।
ठीक है, ठीक है।
जी जी।
आपको और सर को, क्योंकि सर दोनों को दे दूंगा।
आज दे देना शाम को।
गुड मॉर्निंग वर्मा सर, जैसे ही प्रिंसिपल सर आते हैं, हाँ चौबे सर जैसे ही आते हैं आप बताइएगा, बस उन्हीं का हम वेट कर रहे हैं। बाकी शायद प्रिंसिपल्स हाँ ज्वाइन कर चुके हैं, बाकी प्रिंसिपल्स।
मैडम सर पहुंच गया, ज्वाइन करते हैं थोड़ी देर।
ठीक है, ठीक है, ओके ओके। भार्गवी, चौबे सर भी पहुंच गए हैं, और आपकी प्रिंसिपल और राजीव कॉलेज से गोवर्धन से बोलना लाइन अप करके रखें। फिर यदु सर, यदु सर।
हाँ मैडम,
हाँ
मैडम ज्वाइन कर रही है।
ठीक है, ओके ओके।
मैडम 2 मिनट में ना सर ज्वाइन करेंगे, सर आगे हैं, सर से बात हो गई अभी।
ठीक है, ठीक है, ओके।
तो मैं सर के पास ही जा रहा हूँ, मैं अंदर में ही हूँ चैम्बर में।
हाँ ठीक है, ठीक है,
सर जैसे ही होते हैं ना तो।
हाँ
भार्गवी मैडम है ना?
हाँ भार्गवी मैडम है।
मैडम नमस्ते।
Bhargavi madam, are you there?
Yes madam, yes madam,
Okay.
I am.
Okay. And your everything is ready at your end?
Yes madam, principal madam is
okay.
there.
Okay.
मॉर्निंग। हो गए सर का रहेगा पहले।
So you can switch off microphone. Meanwhile, I welcome all the participants who have registered for this seminar. Good morning to all of you. In a short while from now, we will start our seminar, inaugural function of the seminar.
हाँ जुड़ गए सब जुड़ गए। ये सब का नाम अच्छा चालू करना अभी मैडम बोलेंगे।
Yes, Bhargavi ma'am, now we can start.
Thank you, madam. A very good morning to one and all present here for this academic and scientific event. I am Dr. G. Nagabhargavi, Assistant Professor of Physics, Government Pandit Shyamacharan Shukla College, Dharsiva, Raipur, and Organizing Secretary of National Seminar on Advanced Materials and Characterizations 2022, that is NSAMC 2022. Honorable Professor P.C. Chaube sir, Principal, Government Nagarjun PG College of Science, Raipur. Respected Professor Sabnur Siddiqui Madam, Principal, Government Pandit Shyamacharan Shukla College, Dharsiva. Respected Professor Sonita Satsangi Madam, Principal, Government Rajiv Lochan PG College, Rajim. Our esteemed guest, Professor Panigrahi from NIT Rourkela, Professor Avnish Upadhyay from Government Engineering College, Bilaspur, Dr. Ayush Khare from National Institute of Technology, Raipur, other esteemed guests, learned professors from different universities, technical institutes, research centers, and colleges, research scholars, and dear participants. On behalf of organizing committee, I welcome you all to the inaugural session of 2 days national seminar on advanced materials and characterizations 2022 to be organized during 26th and 27th August 2022. This seminar is jointly organizing by Materials Research Lab, Department of Physics, Government Nagarjun PG College of Science, Raipur, Department of Physics, Government Pandit Shyamacharan Shukla College, Dharsiva, and Department of Physics, Government Rajiv Lochan PG College, Rajim. Prayer is raising of one's mind and heart to the God and requesting of good things from God. I request, before formally starting this program, I request my colleague, Mrs. Aditi Rani Bhagat. She is Assistant Professor, Department of Commerce, for the invocation of Goddess Saraswati. Aditi.
जी मैम, थैंक यू मैम। आप सभी को मेरा नमस्कार। हम सब विद्यादायिनी माँ सरस्वती की तरफ अपना ध्यान केंद्रित करेंगे कि वो हमें आशीर्वाद दें कि ये पूरा कार्यक्रम बहुत सुचारू रूप से चल सके। नमो शारदा, नमो शारदा, नमो शारदा माता। नमो शारदा, नमो शारदा, नमो शारदा माता। हे विद्या ज्ञान प्रदायिनी, हे विद्या ज्ञान प्रदायिनी, माँ श्वेत कमल कमलासनी, माँ श्वेत कमल कमलासनी, भवभंजनी मनरंजनी, भवभंजनी मनरंजनी, अम्बा वागीश्वरी माता, हो अम्बा वागेश्वरी माता। नमो शारदा नमो शारदा नमो शारदा माता। बोलो सरस्वती मैया की जय। थैंक यू मैम।
Thank you, Aditi. To welcome is to show honor. To welcome is to show integrity. I request Honorable Professor P.C. Chaube, sir, Principal, Government Nagarjun PG College of Science, to deliver the welcome address and bless us with his words. Sir, please.
I welcome from Government Nagarjun PG College of Science Raipur to all participants for whatever group manager that Material Research Lab Department of PG College of Science Raipur is organizing this seminar. With association with the Pandit Shyama Charan Shukla College Dharsiwa, Raipur and Government Rajiv Lochan College Rajim. This seminar is being organized under the Research Promotion Committee of this college, and it is certainly going to quite beneficial for the academicians and young researchers on new advanced material of technology importance. The list of the speakers is quite impressive, and I appreciate this seminar for participating the our research scholars and speakers, chairpersons, and some other academicians also. It is matter of also great pleasure that near about 50 research scholars are connecting through this workshop, and it will be, I think, very much beneficial to our institutions as well as our professors, research scholars, and students also. I also congrats to our organizing committee, Dr. Anjali Avadia, co-convener B.G. Sharma, Bhubaneswar Verma, organizing secretary G. Nag Bhargavi, and Govardhan Yadu from Rajim. It is very much, I think, effective and impressive. Organization will be, I think, organized by you organizing committee. And this is also very much useful to all of us. I hope it. Thank you very much, all of you.
Thank you so much, sir. Now I request Professor S. Siddiqui, Madam, Principal, Government Pandit Shyama Charan Shukla College, to address the session. Madam, please.
थैंक यू भार्गवी। सभी को नमस्कार करती हूँ। शासकीय पंडित श्यामाचरण शुक्ल महाविद्यालय धरसीमा के भौतिक शास्त्र विभाग, शासकीय नागार्जुन स्नातकोत्तर विज्ञान महाविद्यालय रायपुर एवं शासकीय राजीव लोचन स्नातकोत्तर महाविद्यालय राजिम के संयुक्त तत्वावधान में आयोजित राष्ट्रीय शोध संगोष्ठी नेशनल सेमिनार ऑन एडवांस मटेरियल्स एंड कैरेक्टराइजेशंस NSAMC 2022 के उद्घाटन सत्र में उपस्थित शासकीय विज्ञान महाविद्यालय रायपुर के प्राचार्य डॉक्टर पी.सी. चौबे सर, स्नातकोत्तर महाविद्यालय राजिम की प्राचार्य डॉक्टर एस. सत्संगी मैम, संगोष्ठी में अतिथि के रूप में उपस्थित प्रोफेसर एस. पानीग्रही, रिटायर्ड प्रोफेसर, राष्ट्रीय प्रौद्योगिकी संस्थान राउरकेला, संगोष्ठी की ऑर्गेनाइजिंग कमेटी के सभी सम्मानीय सदस्यगण, विभिन्न विश्वविद्यालयों, महाविद्यालयों एवं तकनीकी संस्थानों से जुड़े प्राध्यापकों एवं शोधार्थियों सहित सभी प्रतिभागियों का मैं हार्दिक स्वागत और अभिनंदन करता हूं। ये अत्यंत सुखद एवं गौरव का विषय है कि हमारे महाविद्यालय में भौतिक शास्त्र विभाग द्वारा इस तरह की ये संगोष्ठी, वो भी राष्ट्रीय स्तर पर आयोजित की गई है, जो कि सराहनीय है। इस प्लेटफॉर्म के द्वारा इस विषय पर शोध के क्षेत्र में कार्य कर रहे सभी शोधार्थियों के लिए एक नई दिशा मिलेगी। साथ ही महाविद्यालय में छात्र छात्राओं को भी शोध के क्षेत्र में अग्रसर होने की प्रेरणा मिलेगी। वर्तमान समय हमारा जीवन प्रौद्योगिकी पर इतना निर्भर है कि हमारी मूलभूत सभी आवश्यकताएं इसके द्वारा संचालित है। इसी प्रौद्योगिकी का विकास निश्चित रूप से एडवांस मटेरियल में हो रहे शोधों पर निर्भर करता है। ऐसे इस महत्वपूर्ण समसामयिक विषय पर राष्ट्रीय स्तर की शोध संगोष्ठी का आयोजन कर सभी विषय विशेषज्ञों को एक मंच पर लाने के लिए ऑर्गेनाइजिंग टीम को मैं हार्दिक शुभकामनाएं देती हूँ। इन 2 दिवसों में विभिन्न संस्थाओं से अतिथि वक्ताओं के रूप में अपना बहुमूल्य समय देने के लिए मैं सभी विषय विशेषज्ञों का भी हार्दिक धन्यवाद करती हूँ और इस संगोष्ठी की सफलता के लिए सभी को अग्रिम बधाई देती हूँ। सभी को पुनः धन्यवाद और शुभकामनाएं। धन्यवाद।
Thank you so much, ma'am. Thank you.
Thank you, madam. Now, I request Dr. Satsangi, madam, Principal, Government Rajiv Lochan, PG College, Rajim, to address this session. Madam, please. Madam, please unmute yourself.
आवाज आ रही है मेरी?
Yes,
जी
madam.
जी मैडम।
जी जी
चलो सर्वप्रथम आप सबको नमस्कार। गवर्नमेंट नागार्जुन विज्ञान महाविद्यालय रायपुर के प्रिंसिपल डॉक्टर पीसी चौबे सर, प्रणाम सर। शासकीय महाविद्यालय धरसीवा के प्राचार्य डॉक्टर एस सिद्दीकी मैडम, नमस्कार। यहाँ उपस्थित समस्त रिसोर्स पर्सन, आप सभी को मेरा हार्दिक स्वागत करती हूँ, अभिनंदन करती हूँ शासकीय राजीव लोचन स्नातकोत्तर महाविद्यालय राजिम की ओर से। यह अत्यंत हर्ष की बात है कि शासकीय राजीव लोचन स्नातकोत्तर महाविद्यालय राजिम, शासकीय नागार्जुन विज्ञान महाविद्यालय रायपुर, शासकीय पंडित श्यामाचरण महाविद्यालय धरसीवा के संयुक्त तत्वाधान में आयोजित वर्चुअल राष्ट्रीय संगोष्ठी में आप सभी का स्वागत है, वंदन है, अभिनंदन है। देखा जाए तो ये एक बहुत अच्छा प्रयास है और मैं बहुत बहुत बधाई देना चाहती हूँ कि 3 महाविद्यालय के भौतिक शास्त्र के विभागाध्यक्ष और विभाग के लोगों ने इस तरह के कार्यक्रम को योजना बनाकर इसको मूर्त रूप दिया, जो निश्चित ही आने वाले समय में एक बहुत अच्छा उदाहरण हमारे पूरे छत्तीसगढ़ के लिए होगा। इस तरह से संयुक्त तत्वाधान में अगर कार्यक्रम आयोजित करते हैं तो उसका लाभ, उसमें जो ज्ञान का प्रसार होता है वो निश्चित ही हमारे विद्यार्थियों और शोधार्थियों तक जाता है। जैसा कि मुझे पता है कि मटेरियल विज्ञान पर आयोजित यह राष्ट्रीय संगोष्ठी जो 2 दिवसीय चलेगी, यह अनुसंधान के क्षेत्र में छात्रों, प्राध्यापकों और शोधार्थियों को उच्च स्तर तक ले जाने में निश्चय ही मील का पत्थर साबित होगी। संगोष्ठी वैसे भी विचारों, अनुभवों और किए गए सार्थक कार्यों के परिणामों को एक दूसरे के साथ शेयर करने का माध्यम होता है और विज्ञान के क्षेत्र में तो अनुसंधान की अपार संभावना है, ये सब हम जानते हैं। सबको मालूम है कि जहाँ पे अनुसंधान होता है वहाँ पे विकास की नए नए द्वार खुलते हैं, विकास को एक गति मिलती है और संसाधन और सही मार्गदर्शन में यदि हम इस प्रकार के अनुसंधान कार्य करें तो बहुत अधिक विकास की संभावनाएं बढ़ जाएंगी। हमारे उभरते हुए छत्तीसगढ़ में अनुसंधान के क्षेत्र में इस प्रकार के जो कार्यक्रम हैं, इस प्रकार के सेमिनार हैं, वो निश्चित ही बहुत ही लाभान्वित होंगे। मैं यहाँ बताना चाहूँगी कि हमारे महाविद्यालय में जो भौतिक शास्त्र विभाग है उसमें स्नातकोत्तर स्तर पर इलेक्ट्रॉनिक्स लैब, प्रोग्रामिंग लैब, अनुसंधान हेतु नैनो स्थित फिल्म प्रयोगशाला विद्यार्थियों के लिए उपलब्ध है। महाविद्यालय के छात्र बहुत ही ज़्यादा मेहनती हैं और अच्छा रिजल्ट लाते हैं। पंडित रविशंकर विश्वविद्यालय की जो प्रावीण्य सूची है उसमें भी वो अपना स्थान बना रहे हैं। साथ ही मैं बताना चाहूँगी कि नेट और गेट परीक्षाओं में भी सफलता अर्जित कर रहे हैं। इस विभाग में अभी वर्तमान में एक ही नियमित हमारे प्राध्यापक हैं, सहायक प्राध्यापक डॉक्टर गोवर्धन यदु सर, पर वो पूरे समय छात्रों के साथ लगे रहते हैं और उनको बहुत ज्यादा नई नई चीजें, नए नए अनुसंधान के दिशा में उनको मोटिवेट करते हैं। पूर्व में भी भौतिक शास्त्र विभाग द्वारा 3 राष्ट्रीय सेमिनारों का आयोजन किया जा चुका है। साथ ही विभागीय गतिविधियों को भी निरंतर संचालित करने का कार्य विभाग के प्राध्यापक और विद्यार्थी भी कर रहे हैं। मुझे पूर्ण आशा है और विश्वास भी है कि यह जो वर्चुअल मोड पे आयोजित नेशनल सेमिनार है, इससे रिसर्चर्स भी लाभान्वित होंगे और साथ ही साथ पूरे छत्तीसगढ़ में एक बहुत अच्छा पैगाम और एक बहुत अच्छा मैसेज जाएगा। मैं सब महाविद्यालय के प्राचार्य डॉक्टर पीसी चौबे सर, सिद्दीकी मैडम धरसीवा कॉलेज के, और साथ ही साथ ऑर्गेनाइजिंग कमेटी और बाकी सभी स्टूडेंट्स को बहुत बहुत बधाई और शुभकामनाएं देना चाहती हूँ, धन्यवाद भी देती हूँ। ये अवसर मिला राजीव लोचन कॉलेज को भी किस तरह के कार्यक्रम में सहभागिता का। मैं आप सबको बधाई देती हूँ और इस सेमिनार की सफलता की कामना करती हूँ। धन्यवाद।
Thank you, madam. Material science is an interdisciplinary field which covers a wide range of science and technology, including physics, chemistry, metallurgy, electronics, etc. I would like to invite convener of this seminar, Dr. Anjali Audhia, to present the outline of this seminar and also to discuss the theme. Madam, please.
Namaste, a very good morning to all of you. I welcome on behalf of the organizing committee of this national seminar, I welcome all the dignitaries, our invited speakers, keynote speaker, Pandri sir, Manoranjan Kar sir, Alka Garg ma'am, and our own Ayush Khare, ML Verma sir, respected principal sir, Dr. PC Chaube sir, principal of Government Nagarjuna PG College of Science, who has been a constant source of inspiration for organizing this kind of seminar, a joint effort, and principal Dr. Shabnoor Siddiqui ma'am, Government Pandit Shamacharan Shukla College Dharsiwa, principal Dr. Sunita Satsangi ma'am, Government Rajiv Lochan College Rajim. I am taking this opportunity for to thank all these principals and head of the institutions of our government colleges for undertaking this commendable initiative to gather academicians and subject experts contributing in the field of new technologically important advanced materials. I am delighted that NSAMC 2022 conference provides a platform for all stakeholders in the field of research and education, which include policymakers, academicians, researchers, and last but not the least, for the students pursuing physics, chemistry, or science in their post-graduation, to share experiences and exchange ideas on contemporary issues affecting the new technologies and fundamental concerns related to new advanced material science. I believe that this conference will generate new ideas, innovations, and strategies to address the challenges researchers face during their journey. This seminar is innovative and noteworthy in many ways. The theme is multidisciplinary, covering every branch of science, as there has always been a constant search for new materials and technologies. The imperative of advanced material research is essential in realizing the much desired Atmanirbhar Bharat through Make in India and skill development drives. Thirdly, this seminar is organized under the research promotion policy of our colleges to inculcate a spirit of inquiry in young students and researchers through a lively interaction and lectures delivered on relevant topics. I strongly believe that by merely attending a seminar of this kind and listening to speakers chosen from the plethora of finest academicians and researchers, students and young researchers will be motivated and will get many new ideas which will enhance their own research skills. Our organizing team members have been working round the clock to make this seminar a success. I would like to use this opportunity to assure that this team will continue to provide more opportunities through joint ventures on quality research and commit more to the purpose of providing a genuine platform to young researchers and science students for sharing their ideas and learn from subject experts. As I look forward to robust discussions and recommendations that would proceed from this conference, let me remind you not to undermine the power of such noble endeavors as it shows the path for collaboration and joint efforts. ये मैं जरूर highlight करना चाहूंगी. This is a collaborative effort, and all the principals are here to bless us. And this is a great movement for all the organizing team members. So you should not undermine power of such noble endeavors, as it shows the path for collaboration and joint efforts to combat the lack of financial resources and manpowers. Together we can and we will. I believe that it is the engine that will propel us into the much anticipated growth and development in the field of research. I thank all the distinguished speakers, guests, colleagues, researchers, students, and well-wishers from all over India for supporting us through their presence and overwhelming participation, giving a truly national character to NSAMC 2022. Once again, welcome and thanks for all your support and overwhelming response from all corners of India. Thank you so much to one and all.
Thank you, Adhya madam. Now it's time to release the book of abstracts. I request all the three principals, Professor P.C. Chaube sir, Professor Siddiqui madam, and Professor Satsangi madam, to release the book of abstracts. Please switch on your camera so that we can have a click. All of you, please, I request you to switch on your cameras so that we have a nice click.
भुवनेश्वर सर, कैमरे का एंगल थोड़ा डाउन करेंगे क्या, तो सर के हाथ में वो बुक दिखेगी अच्छे से. The editor of this book is Dr. Bhargavi.
बोल दूं क्या?
हाँ, थोड़ा सा.
Yes.
नहीं मैम, फ्रंट ही
ऐसे
करिए.
नहीं, तो पूरा यही.
मैं आपको जरूर बतलाना चाहूंगी, all the abstracts have been edited by Dr. Bhargavi and her research scholar Pavan Kumar. They have worked day and night for making it happen at this moment, and we are with 50 abstracts, and here is my Department of Physics. All the members of Department of Physics are present at our college, Science College. Thank you. Thank you so much.
Just a minute, madam. I am clicking on. Yes. Thank you.
Thank you, P.C. Chaube sir.
Thank you, madam. Thank you,
Satsangi
Chaube
ma'am
sir.
and Siddiqui sir. Siddiqui ma'am, sorry.
Now we are ending towards the stepping towards the end of the inaugural ceremony. Before formally ending this ceremony, I would like to invite Dr. Govardhan Yadu from Rajim Government PG College of Rajim for vote of thanks. Sir, please.
Thank you, madam. Good morning, all. I feel honored and privileged to get the opportunity to give a vote of thanks on this special occasion. I would like to thank all the honorable delegates who blessed us with their presence. I am also very much thankful to all program advisory committee members and invited speakers. Words are not enough to thank their constant guidance and support to shape the seminar. I, Dr. Govardhan Yadu, behalf of the organizing committee, convey deep regard and heartily thank to Honorable Dr. P.C. Chaube sir, Principal, Government Nagarjun Science College Raipur, Honorable our Principal Madam Dr. Samita Sasangi, Principal, Government Rajiv Lochan PG College Rajim, and Honorable Dr. S. Siddiqui Madam, Principal, Government College Dharsiwa. They help us in obtaining the necessary administrative approvals for organizing the event in virtual platform. They support in all possible manner to organize this seminar. I am very much thankful to all the resource person, chairperson of the technical session and participants for making this event a memorable and remarkable one. I am very much thankful to all the faculty members, students, research scholars, technical staffs and non-teaching staff of the Government Science College Raipur, Government Rajilochan College Rajim and Government College Dharsiwa for his constant help and guidance that radiate a source of energy within us. At the end, but not least, I would like to take this opportunity to thank my nuclear counterpart of the organizing committee heads, Anjali Odhya madam, Bhargavi madam, Verma sir, BG Sharma sir, and members of all the organizing committees who always stand by us and motivates us. If time is money, then today we have spent millions for us. Thanks to all of you for making this event successfully. Hope you will enjoy today national seminar at the virtual mode. Thank you very much.
Thank you so
Yadu.
much.
Thank you, Yadu sir. So this is the end of the inaugural session. Now we proceed towards the first technical session, and the chairman of first technical session is among us. So, madam, shall I start the first technical session?
Yes, sure.
Yes. Dear participants, please stay with us. This is the first technical session, and chairperson for this first technical session is Professor Avnish Upadhyay. Sir, are you able to listen me?
Yeah, thank you, Bhargavi.
Yes, sir. Sir is from Government Engineering College, Bilaspur, and he has a vast experience of research and teaching. Sir, without delaying, I would like to hand over this session to you, sir. Panigrahi sir is among us.
Okay. Thank you, Bhargavi, and thanks the organizing committee for giving me this opportunity. So on behalf of the organizing committee, I welcome you all in the very first session of this conference, Virtual National Seminar on Advanced Material and Characterizations 2022. This seminar is being organized by jointly by Government Nagarjun Puji College, Government Pandit Syamacharan Shukla College Dharsinga, Government Rajiv Lochan College Razim. In this very first session, we have two talks. The very first one is the keynote address, which will be delivered by Professor S. Panigrahi, and then we will have invited talk, which will be delivered by Dr. Manoranjan Kar. Professor S. Panigrahi is currently working as a capacity of senior professor in National Institute of Technology, Roorkee. He has a very vast experience in research and teaching. He had around 200 publications in last 5 years in his credit. He have completed 2 major projects, 2 minor projects is being run by him. This is being done. He is author of 6 books, and 2 books he have written, which is in press right now. 16 students have been completed their PhD under his guidance, and 2 is being guided by him for their PhD. They are pursuing their PhD under him. And he has visited many countries like USA, UK, Australia, South Korea for the academic purposes. He is doing his work in the field of ferromagnetic materials, dielectric properties of electroceramics, and thin films. It's my privilege to invite such a learned person to deliver his keynote address for this very much seminar. Panigrahi sir, please. Professor Panigrahi sir, please.
Yeah.
Thank you, sir.
Am I audible?
Yes, sir, very much.
Yes, sir.
Am I audible? Okay.
Yes.
Share your entire screen. ठीक है. अच्छा, मेरा पावर पॉइंट निकालना पड़ेगा ना. Power point is this one. Am I audible?
Yes, sir. We can hear you.
Yeah. I am sharing my end here. Click. इसमें save. Which one I will say? Could you able to see my slide?
Yes, sir. Yes, sir. You can make it full screen now.
Okay. Am I audible?
Yes, sir.
Yeah. Thank you. I am Professor Panigrahi, from retired professor of physics from NIT Rourkela. At the outset, I thank you all for giving me this opportunity, particularly the organizing committee of the government Nagarjun PG College and other sister PG colleges of the Raipur. And am I audible, madam?
Yes, sir. Yes, sir. Everything
Hello?
is fine.
Yes,
You
yes,
can.
sir.
Everything is fine. Okay, sir.
If you find any trouble, then you let me know. If I don't hear any signal, then I presume that I am audible. Am I correct? Hello.
Yes, sir.
Hello. Rightly, I am in a discomfort position. I just accepted the offer, but now I am at Delhi for some important work. However, because I have already assured, I am the talk is not properly organized, but I will try my level best to make it as far as practicable. I am little comfortable because you have given a keynote talk. Keynote talk is very easy to give because the coverage is breadth, not the depth. I will tell you something about many things, not everything about something. There are two ways of disseminating knowledge: telling something about many things, telling many things about a focused thing. And because of it is a keynote talk, and this being the first talk, it should be very comfortable. Everybody can listen it without any tense, and everybody they know it is not that it is just a compile of what you know in a pedagogical approach. You might be aware that being a teacher, no matter how tough will be the examination, the first question should be such: all the candidates should smile. Similarly, this being my first lecture, first talk, and that too also keynote talk, everybody should listen with less tense and smile. And my title is the Pillar of Material World. As you know, you have given a seminar. Your seminar is entitled Synthesis and Characterization. If you find all the material science thesis, 80% of the thesis goes synthesis and characterization of Mr. XXX, something. So what does it mean? Synthesis and characterization are two pillars for the material world. Next slide. You know, as you know, from the time immemorial, mankind has been attracted to the world of material. That is why civilization marched from Stone Age, Copper Age, Bronze Age, Iron Age, and synthetic material age. Every morning we hope for a new material, which are much finer and more comfortable than its previous night. Yeah, then the question comes: why do you bother about the new material? Why scientists every morning wake up with the purpose of getting a new material? What are difficulties with the old material? In spite of the nature is gifted with iron, copper, manganese, all natural resources and minerals are available. What bothers us to make a new material and how they were improved? It is that with the new improved property, we are always interested with the improved property so that it will be a mark the progress of the civilization. The material has an enormous impact for the lifestyle and work style of the people. Now, nature has given everything to us, but three major macroscopic property of the material: hardness, stiffness, and toughness. They are mutually incompatible. No material possesses equally hardness, equally stiffness, and equally toughness. At least you get only two property, but it is completely impossible to get all the property in the same material. That is why the natural material, in spite of the large resource of natural material, we should march ahead for the synthesizing new material. And now, what are the basic property you want? What do you mean by hardness? Hardness is the tensile strength, that how much largest force the material can withstand without break. Stiffness is called the elastic moduli, and toughness is the resistance to for the crack movement. And all the three cannot be obtained in the same material. It is very difficult any two of them in the same material, but almost impossible to have all of them in say, one natural material. So you need a optimum compatibility of three. In order to make a optimum compatibility, you have to tailor, monitor crystal structure, molecular structure, macroscopic structure, electronic structure, ion transfers, material constant. Is it okay, madam? Is it okay, madam? Hello?
Sir, it is okay.
Yes,
Hello?
you're audible. I would request all the
I'm finding
participants to
some.
kindly mute themselves.
Yeah.
Yes.
So now what are the improved property? Improved property being lightweight. The material should be lightweight, hard, stiff, tough, crack resist, fracture resist, corrosion resist, temperature resist, and strength to weight ratio. And also the material should be cost effective, that is affordable. So now what are the new material now? Polymer, ceramic, superconducting, nano material, composite material, soft material, cluster, intelligent material, spintronic material, biomaterial, organic material, ferroelectric material, magnetic material, smart material, intelligent material, whatever you call it to be. So
So your sound is breaking, voice is breaking.
marching of the depending upon they bring a different form. Maybe my voice is breaking. So you need the preparation or synthesis of bulk, thin film, and nano. The pedagogical approach of my talk is what are the different routes for bulk preparation, thin film preparation, and nano preparation. As I've already told, since it is a keynote talk, I will tangentially touch everything. The most common conventional way of synthesis the material is solid state, sol gel, co-precipitation, autocombustion, hydrothermal, many more. The list is not completely exhaustive. But however, depending upon time, because I have to go another 50% characterization, I will tangentially touch with the methods. Now, these are for the bulk preparation, this general procedure of processing is you have to take the raw material, mix it in a stoichiometric preparation, then you need calcination, then you need milling, then you need binder worn out, sintering, walling. After that, the material will be ready and you will subject to characterization. And this is just raw material. So, and now you see desired stoichiometric proportion of the precursor and mixed by ball milling, then calcination, then by XRD you have to confirm the phase, then cold pressing, sintering, everything. Now this is all about a schematic chart or a flow chart for a solid state reaction, and among all the reactions, solid state route is more convenient and it is also font friendly. And now the another method is what you call the sol gel method. Sol gel is it is a chemical solution process. Sol gel process is very long known and it is versatile technique. Sol gel is a chemical solution process used to make ceramic glass material, maybe in the form of thin film, fiber, and powder. What is a sol? Sol is the dispersed colloidal particle. The dispersed phase so small, the particle is a size of the colloidal size. It is so small, the gravitational force do not exist. Because the gravitational force do not exist, the particle will not settle down and they will float. Force equal or the molecular suspension of solid particle of ions in a solvent. Gel is a semi-rigid mass that forms when solvent from the salt begins to evaporate. If the solvent gets evaporated, then you get left behind this condensation reaction of the molecular precursor such as metal alkoxide and inorganic salt. It is practically hydrolysis solution. This is what is the flow chart of the precursor, then solution, then dehydration, then drying, then you can get for spinning, calcination or suspension, powder. If you want coating, you will come to this film coating, powder, and you can get the bulk form of the dense syrup. This is the flow chart of how sol-gel process works. Now, these are the two methods I have given under the preparation of bulk. One is the solid-state reaction, other is the sol-gel. But there are many more methods. And now let us come what do you mean by a thin film. Bulk, thin film, nano. These are the three different forms of the preparation. Each has own merit. Then why do you go for thin film? And what is the merit of thin film over the bulk? This transparency will tell you. When the material is in the form of thin film is nothing but one-dimensional nano and two-dimensional bulk. That is, and more surface setup, high purity, high current density, surface-dependent property, smaller size, visible light, increased bandwidth, controlled deposition, like that. These are the merit of the thin film over the bulk. And these are the application. Application, electrical conduction, semiconductor, solar cell, optical film, tribological coating, energy conversion, magnetic field, diffusion barrier, corrosion. So endless is the application of the thin film. So it overweighs over the bulk form of the material in many aspects. More so miniaturization. Material amount is very less, and you will get more property. So efficiency, monetary efficiency will be there. So for that you need a substrate, and this is the substrate, and this is the film. And what are the property of the substrate? Chemical stability, hardness, and these are that, and this is that. So what are the different
No connectivity.
preparation method. I have to tell something about everything, not everything about the something. So okay, disturb kariya from 10 minutes. So audible na nahi
Yes, there was some problem, but now it's okay, sir.
Now it is okay.
Now it's okay.
10 minutes. Now let us come to the PVD, physical vapor deposition. Among the physical vapor deposition, this is the flow chart. So what you do is that the solid or liquid in condensed phase, it will be evaporated to gas phase, then it will be transferred to the gas phase, then it is condensed and condensed phase. So it will go from condensed phase in the form of bulk to the condensed phase in the form of thin film. This is the transport. Evaporation followed by condensation is the physical vapor deposition. It's a very simplest method. And what are the types of evaporator? It may be thermal evaporated or electron beam evaporated. This is what is called the thermal evaporation. Material is there, it will be heated, it will be evaporated, and they will be deposited on the substrate. But telling is easy, but doing is very difficult. It is not that easy as it seems to be. So what you need, vacuum you required, it should be low cost, wastage of the material is less, low temperature deposition, and this is what is called the schematic diagram of a thermal evaporation. And electron beam evaporated. There is an electron gun, so heating will be done by a electronic beam. And Here also you required a vacuum, but contamination is less. So why vacuum is required? If the chamber is vacuum made, then the mean free path will be more. That means a particle can move from one place to other without any suffering any collision. If the vacuum industry will make a strike, thin film industry will also stop doing. So this is what is called the E-beam evaporator. Then next we will go to the sputtering, and process. It is a process where atoms are ejected from the solid material due to bombardment of target by non-reactive energetic particle. So non-reactive energetic particle will hit the metal or something like that. So advantage, these are the advantages of the sputtering: low thermal budget, large area growth, film quality is good, and less chance of contamination, everything. So this is the mechanism of sputtering. So inert gases will hit the metal, and it will be, there are different processes involved, interaction of ions with surface. This is just a sputtering. Incident ion, and this is the sputtered atom. So the incident ion hit the metal, and ultimately you get the sputtered ion, sputtering. And now let us come to the PLD. Pulse laser deposition is a physical vapor deposition process which is carried out in vacuum, but the here is hitting is done by a laser beam, high energetic laser beam. This is what is called the PLD. Laser beam hit the metal, and atoms and molecules are collected, and ultimately thin film will be prepared. This is PLD. Then what is called the another is molecular beam epitaxy. In other method, there is no intrinsic relation between substrate crystal structure with film structure. That is why there may be a very mismatch factor. But in molecular beam epitaxy, the structure of the thin film and the structure of the crystallographic structure of the target, there is a matching. So that is what is called the matching factor is high. So it is called the epitaxial growth. This is the just molecular beam epitaxy. Now this is all about the thin film. So I completed bulk, I completed thin film. Now I will go to the nano material. And nano material, as you know, these are the very simple. Nano material is of the order 10 to the power 9. And this is how small is the nano. You can know from this. And this is just a nano is more, it is Feynman told that there is a plenty of room at the bottom. Whole Britannica can be written in the tip of a fingerprint or a pin. So nanotechnology, the Feynman in the year 1959 could imagine that there is a plenty of room at the bottom. We should not think of bulk. The small is also good. So what are the property of the nano? That tripletants, you know, there is a drastic change in property. The main two reasons for the property change when the material brought to nano is that surface to volume area. Area is more compared to the volume. And second is when the particle brought to the nano stage, there is a quantum confinement. So the excitation or the band gap, you can tailor it as per your need. So this is the, so there is a drastic change because of the two physical reason. There is a drastic change in the when you go to the into the very large scale integration. So tomorrow, according to the Morris law, every day or every year the chips, number of chips in a compact disk number goes on increasing. So naturally you have to find a material to meet that requirement. As you know, for the nano, always you are carried by an impression that the material property doesn't depend upon the size dependent property. Whether you take 1 kg of iron or 10 gram of iron, its specific gravity, its density, its everything, what you call it, to the thermal conductivity, everything will remain same. And color, but that doesn't hold good. It stops holding good when it is brought to the nano stage. For example, gold is yellow always. Whether you take 1 kg of gold or 1 gram of gold, it is yellow. But when gold will become nano, when the gold size is 300 to 500, it will become blue, red. So gold is not always yellow. Gold is yellow up to our perception. But when it comes to the nano structure, gold will be different color. So then how to prepare? Now let us come how to prepare the nano material. There are two broad classification, what is called the bottom-up approach and the second one is top-down approach. Madam will tell you how much time I left so that I will still make, because my number of slides may be as many as 100.
So
Now you tell me how much
you have around 40 minutes, sir.
I completed a 40 minutes. I am left with 40 minutes.
No, you have completed 24 minutes and another
Okay.
40 minutes.
Okay. I am comfortable. I am comfortable.
Okay.
Now, basically, there are two methods: top-down methods and bottom-up approach. And as you know, from bulk, if you go from top-down to bottom-up, it is either ball milling, that is called the physical process. But if you come from bottom to top, it is a chemical. So physical top-down, by physical mechanism, you can take bulk and go on dividing it until you come to the nano stage. And by chemical route, you add them up, go to the nano. 1000 atoms can be agglomerated. And now these are the basic property of nano material. So now I completed almost the synthetic part. Bulk, thin film, nano. In bulk, solid state reaction, solid reaction. In thin film, PVD. Particularly, I concentrated PVD, CVD, and others I left. And similarly, coming to the nano, I just covered bottom up and top down. Now I the desire of material scientist, you know, everything what you are bringing in thin film or nano, or there is an internal change in the parameter, you cannot see. God gifted eye has some limited magnification resolution. Everything you cannot see. So you only characterize it so that you can see. So characterize, almost all characterization techniques are visible eye for invisible world. The world, everything is not visible by your God-gifted eye. There is an invisible world which you cannot see. When you cannot see, you have to see. Otherwise, because seeing is believing. Unless you see, you cannot believe it. So you have to think of by certain characterizing technique so that you can see the invisible world. So almost all characterizing techniques are based upon the principle visible eye for invisible world. Now what happened? You need some excitation in order to see. Just like in order to see bulk, a light has to fall on the bulk material, it get reflect and fall on your eye, give sensation in your retina. Similarly, you have to choose some exciter or probe. Probe may be X-ray photon. If the probe may be X-ray photon, we have XRD, XPS, XRF. If it is a visible photon, FTIR, PL, and Raman. If it is electron beam, SEM, TEM, STM, and AFM, it may be a neutral beam or ionized radiation. And now XRD characterization. What XRD can tell you? Suppose you want to mix or suppose you want to dope. You take a perovskite structure ABO3. Suppose you A has to be replaced by A prime or B has to be replaced by B prime. You want to prepare A prime BO3 or A B. So what you have to first ensure whether the phase formation or so it will tell you whether secondary and similarly single phase implies the if the phase you get single phase, it will tell you the dopant has diffused in the host. The symmetry of the peak, you can calculate ABC lattice parameter, and if after doping peak position shift, there is a change in lattice parameter. After doping, lattice parameter ABC gets changed. You can calculate D spacing. You can order of crystalline structure. You can also find the crystallite size using Setter's formula. Characterization, okay. Now you see, suppose barium is replaced by bismuth. I have taken, there are thousands, there are countless number of papers, but I have taken one, two. So XRD will give you phase purity, SEM will give you surface morphology, EDX will give you chemical analysis. So I think this talk will be very interesting for the beginners, but those who are well-established research scholar, it is just a wastage of time, I feel. But those who want to, my objective of keynote talk is not to help those who know, but to help those who start knowing. Those who are just the, what do you say, what do you call the Noria. Those who start doing something, it will be very useful. So this is what is called the, you see, suppose you want barium, bismuth, titanate, you have to take barium carbonate, titanium oxide, bismuth oxide, mix it, ball mill it, calcinite it, and you have to do an XRD analysis for phase conformation. Then you have to sinter it, you density. Then you have to again do XRD to confirm the phase formation, then characterize. And you see, this is one of these XRD plot, and here you find 2 theta, full width half maxima, A, B, C, all are the lattice parameter. You can find C by A ratio, packing fraction, and crystalline size, lattice strain, and everything you can find out. And this is what is when doping concentration. You can dope the material with different concentration when the change in doping concentration and lattice parameter. Similarly, change in doping concentration by C by A ratio. And these are the, and also you see when the doping concentration will increase, then lattice strain will increase. However, the crystallite size will decrease. And similarly, by using this particle size, you can using by this error formula, where lambda is the X-ray wavelength and theta is the glazing angle and beta is the full width half maximum distance, so that you can find the average crystallite size. Similarly, you can UV visible spectroscopy. By visible spectroscopy, you can find wavelength versus observance. Similarly, and these are the fluorescence and XRD analysis. Similarly, this completes your XRD, which is a fingerprint technique for any general material scientist, not necessarily a particular group of material scientists, because if you want to do something, or it is a kitchen in an Indian kitchen, and also it can be equivalent to a surgery. So you make a atomic replace the surgery department of the medical college, hospital. You take out your disease organ and replace it. Similarly, you take something from the host material, parent material, natural material, and replace it with something. Now the next one is X-ray photoelectron spectroscopy, XPS. It is a quantitative spectroscopic technique that measures the elemental composition, chemical state, empirical formula, electronic state of the element. It works on the principle of the photoelectric effect when soft X-ray is used in exciting probe. XPX spectra are obtained by irradiating material with a monochromatic beam of X-ray, while simultaneously measuring kinetic energy and the number of electrons that escape from the top 1 to 10 nanometer. So what you do, you irradiate with the soft X-ray and measure simultaneously the kinetic energy of the electrons coming out from the top 1 to 10 nanometer. It is a tool to study the nanostructure 2D material. Then the third one is X-ray fluorescence spectroscopy, XRF. Here what happened, electron is ejected from the K cell by the incident X-ray photon. Similarly, X-ray photon is bombarded and electron is ejected from the K cell, resulting the emission of X-ray quanta. And analysis of X-ray of various elements, it can give you to analyze the element present. Similarly, just like X-ray, you can also use visible light. Using visible light, you can have FTIR, Fourier transform infrared spectroscopy. The molecular structure of the functional group is like the skeleton of a material. Just like human body has a bone skeleton, similarly, if you take the functional group, is the skeleton of the molecular structure is the skeleton of the functional group. FTIR spectrum is obtained due to absorption of electromagnetic radiation of certain frequency, and this is correlated to molecular vibration and chemical bond. It gives the presence of aromatic ring, functional group, location and orientation of molecule within the structure. Similarly, other one is the photoluminescence, PL. It is a spontaneous emission of light, either fluorescence or phosphorescence, that depend upon the time period of emission. If it is less than 10 to the power minus 8 second, it is fluorescence, and other one is the phosphorescence. Now, it is due to the energy transfer of the radiation to the electron, leading to the excited state, and further coming is excited from the ground state to the comeback. So while come back, it will directly come to the ground state, then it is fluorescence. And if it come from a metastable state, if there is a three-state transition, excited to metastable, metastable to ground, it is phosphorescence. So these two are, this is the fluorescence spectra, wavelength and excitation, and similarly wavelength, and this is called the emission. Then the another is the Raman spectroscopy. It is also versatile experimental tool to prove the local structural change, such as lattice distortion, octahedral rotation. Suppose ABO3, there is octahedra, and there is a rotation of octahedra. Raman spectroscopy. It is an ideal tool to investigate spin-phonon interaction, electron-phonon coupling, and this is what. Now this is all about your all the excitation, X-ray, visible light, and everything. Now what you see, how to see, this is how to sense it. Now how to see, because you have, as I have already told, God gifted has a limited resolution, so you need an optical microscope. So now coming to the optical microscope, partially opened the gate of invisible material world by inventing first. So microscopic development is from optical microscope, from TEM, SEM, then scanning probe microscope. It may be STM, scanning tunneling microscope, atomic force microscope. So starting from optical microscope, we are going to AFM, and that is what is the what you call it to be. This is the gate. Really, optical microscope opened the gate of the invisible world. Now people are pondering and marching ahead to see everything, to feel everything, to touch everything. Not only that, seeing is believing, touching is the feeling. You need two things. You have to touch the atom. You have to play with the atom. You have to guide the atom. You have to position the atom. It is not sufficient only see. We have to sense it. We have to touch it. Just like when a baby comes out from the mother's womb, the mother is anxiously waiting to see the baby. But he is not satisfied by seeing the baby. He kissed the baby. He touched the baby. He feed the mother's see. Both should go together with a philosophy, positioning everything. And now, as you know, SIM characterization. What SEM does, it will give you the size of the grain, and when you go on doping, what change will happen, and compactness of the grain, density of the sample, grain size, like that. And also SEM is attached with EDX, that is compositional analysis. By EDX made SEM versatile and non-destructive. The interaction of electron beam with sample produces characteristic X-ray of the spectrum. On comparing the energy of and intensity of the characteristic X-ray, one gets elemental composition of that sample. So SEM has two things. You have to see the microstructure, and you can also find the composition, elemental composition of the compound. You see, this is one of the SEM image, and this is what is called EDX analysis. And EDX data, you can find what is the percentage of everything. And how the electron microscope work. Now this is the flowchart of, when an incident beam interact with the sample. There are many, there may be secondary electron, there may be primary backscatter electron, there may be X-ray, and like that. So this is the how a incident beam interact with a sample, giving the primary backscatter electron. Then the cathodoluminescence, it will give you electrical information. Secondary electron, it will give you topographical information, like that. So this is your scanning electron microscope. Here what happened, there is an electron scope, a filament is heated, and it will hit the sample. Just like in optical microscope, you have to focus the photons through a glass lens. Similarly, in scanning electron microscope, you have to focus it through either electric field or magnetic. Normally, magnetic field will more use for focusing the beam of electron, and thereby resolution, everything will be increased. And similarly, now you come to the scanning probe microscope. Scanning probe microscope means it is help to see the atom, play with the atom, and positioning the atom. It may be scanning tunneling microscope and atomic force microscope. Scanning tunneling microscope is a quantum phenomenon because when a tip of the SEM moves over the surface, the wave function of the tip atom and the wave function of the surface atom, they overlap. Due to overlapping of the wave function of the tip atom and surface, and we have two positions remaining tunnel current constant if you vary the distance, and this by scanning the tip, the picture of the surface topography can be made, and from the variation of tip height also you can measure. Principle of it is called the quantum mechanical tuning. It is, you see, scanning tunnel. This is the tip atom and this is the surface atom, and there will be overlapping of that. Everything you can know it by reading the material which you normally found in the standard. These are available in the website also. You can find these things. Only thing is that I will give you a surface coverage of. Similarly, you see, this is atomic force microscope. This is just a cantilever and this is a pointer, this is a sample, and there is a force between the van der Waals force between the sample, and because the force is very smaller magnitude of the order 10 to the power minus 8, the cantilever should be light, and it is first focused to the photodetector, and once the pointer get deflected, the position get distorted. So by scanning, by monitoring or by feeding it to a computer based software, you can sense the position of the atom. This is atomic force microscope, and these are the different, you see, atomic force microscope. This is a laser beam, this is a tip, and this is a light pointer. The laser beam is focused because how much the force is very of the order of 10 to the power minus 7. You cannot measure the force. You have to do by some optical mechanism by the deflection of the pointer. And these are the different operations of the FM. That is what is called image mode and atomic contact mode, non-contact mode, tapping mode. These are the three different modes of the FM. And this is what is called when there is a distance between the tip atom, it is maybe a repulsive, maybe attractive. So this is what is called the contact mode, this is tapping mode, and this is non-tapping mode. This is atomic force microscope. Now with this, we have got all preliminary characterization. Now you come to the specific characterization. If you go to the dielectric material, ferroelectric material, piezoelectric material, multiferroelectric, where there is a combination of magnetism or ferrites as well as the ferroelectric material, you need some specific dielectric measurement. So what you do is that, where from this comes? Here you use dipole as a probe. It was exit. But here the probe is a dipole. Dipole is nothing but the separation between the positive and negative charges. So historically, one greatest scientific achievement of our time has been understanding correlation between macroscopic quantity and microscopic nature. You know, there is some macroscopic parameter and microscopic nature, configuration. So the relation between macroscopic parameter with the microscopic parameter can be carried out using a probe. So all dielectric, ferrites, magnetites, and multiferro, you need either a probe with the magnetic moment of an atom, or it is a dipole separation between the positive and negative. Dipole is the result of electrical polarization. Polarization may be of different, ionic, dipolar. These are the two parameters, dielectric constant and dielectric loss, tangent loss. And you can have capacitive character, you can have conductive character. And there are two stimuli for dielectric: temperature and electric field. You have to vary the temperature with the frequency constant, or vary to frequency with the temperature constant. So two stimulus that a dielectric material response is the temperature and electric field. And these are the just understanding that length I should not be. This is the tangent, real part, imaginary part, tangent loss. Okay, I need not. May I know how much time left? Hello? Am I audible?
Sir, you have more 15 minutes.
Oh, okay. But I will not take 15 minutes because I am some urgent meeting. They called me frequent time. I am one leg is in the seminar hall and other leg is the meeting place where I am assigned some very confidential work. So dielectric it will take, it is what do you say, P loop. Dielectric I can just skip, and complex impedance. My students are also there. What I find, Tanma Bodapanda and Ilasuna Sanjeev may be there. Tanma, are you present? Hello?
No, sir, he is not.
Tanma?
No, sir, he is not present here.
Anyway, anyway, because some more important work is left behind and they are calling me. Okay, I once again thank you very much for giving me this opportunity. I fully understand this talk will be useful for the beginners only, and those who have already completed approach, how they meet the beginners, audience, MSc, BSc student with all their concept. It is just a material synthesis and characterization, a pedagogical approach. This is. Thank you very much for giving me this chance. I am leaving. I am leaving it. Stop sharing.
Thank you, Professor Panigrahi, for your nice talk. Hope this talk will be beneficial for the students, especially those who are going to start their research work, PhD, and also for the students of the postgraduate. As sir has completed his talk 15 minutes before, I would like to invite Dr. Kerr if he is available. Dr. Kerr?
Sir, he is not. He has not joined yet. So can we take a break of 5 to 10 minutes so that we can start again? Anjali madam, Audhya madam.
Or if we have some questions, maybe. But sir is not there.
But sir is not.
Who will answer that?
So can we ask Kar sir to join earlier?
Yes, madam. I will.
Yes.
Okay. So please stay with us. We are trying to get the next speaker on in the seminar in just 2 or 3 minutes. We will let you know if we need a break or we shall continue. Meanwhile, with permission of the chairperson of this session, I would like to intimate about the details of oral talk sessions, because we had more than 45 or so presentations. So we had to organize a separate session for 12 or 13 talks so that it can be completed within time. So the oral talks, as the technical session and program or schedule you already have, it will be organized. Today there is no problem. There will be only one session after the invited talk of Dr. Alka Garg, the oral presentations of Manojit De, Praveen Kumar Litoria, Kamlesh Thakkar, Sangeeta Basak, Devendra Kumar, and after a tea break, Dharamveer, CM Nandanwar, Nisha DM Parshuramkar, A.N. Yarpude, Priti Balatak, and Amrita Nayak, Sakshi Sharma, and Parvati Nayak. So we will have 14 talks in today's technical session after the break, after the lunch session. And for day 2, that is on 27th, we will have one session from 10 to it's I think 10 to 1:30, and then there will be another session 1:30 to 5, and 1:30 to 4 actually, and a separate session will be organized, parallel session will be organized for remaining talks, so that we can cover all the presentations. And I would like all the participants who are willing to give their presentations, give their consents, and be ready with their talk, so that we can smoothly run the technical sessions. So Bhargavi ma'am, do we have any?
Madam, sir has joined.
Okay,
Sir is there.
thank you so much. So I would request Avnish Upadhyay sir to continue with the session.
Okay, thank you, madam. So the second talk in this session will be delivered by Dr. Manoranjan Kar. Kar sir is presently working as an associate professor in IIT Patna. He obtained his PhD from IIT Guwahati in the year 2004. Sir has more than 150 research papers in reputed journal, has a very vast experience. Nine students have completed their PhD under his guidance, and one is doing his research, pursuing his research. The topic of the sir's invited talk is just a moment. Tuning of magnetic properties in ferrite-based magnetic composites as advanced material for modern technological applications. So I invite Professor Kar to deliver his invited talk. Professor Kar, please, sir.
Okay, thank you, Professor Upadhyay, for giving a brief introduction. So, I hope I am visible.
You are visible.
Yeah. So, just a minute. Let me share my slide. Is my slide visible?
Yes, sir. Yes, sir. It is visible.
Very good. I hope it is full screen, right?
No, sir.
Okay, we can go ahead, please. Okay, thank you very much for a short introduction. And it is not the matter. Matter is that what we are going to learn, and in this 1 hour talk, and also thanks to the organizer to start the talk in time, and it was 12:30 and we are in time. So thank you very much. And basically today I'm going to talk about the tuning of magnetic properties in ferrite based magnetic composites as advanced material for modern technological application. So basically, as you know that I am a physicist, you may have heard that I am from physics department, and we'll look into that. Means as a physicist, how I can look at the material's property and how I can tune its property so that we can utilize it for the technological applications. Before going to that, and it is a very highlighted topic of the solar cell and all these things. It is a very hype topic in the nowadays. The people do lots of research on it, but we ignore that because it is not visible immediately to the people that exactly this magnetic field, what it is doing. Only is it only for the magnet, bar magnet in our laboratory or outside. But you believe me, and in the today's world, and you will be surprised to know that without magnetic material and none of the technology is possible. You just look at your remote sensor, it is totally based on the magnetic sensors. Totally no remote sensor is available without any magnetic component or the magnetic material. So this permanent magnetic material has a lot utilization. You look at your vehicle, and there are the now the people are in India, they come little late, and now the others is coming, and all those things are sensor technology are incorporated in our vehicles now. Earlier it was not there, and we are very happy with the means heavy engineering vehicles. But nowadays it is, we call it is the electronics, but exactly there are the means day by day we are requiring the spintronic materials, spintronic. But the question is coming that what I can do as a physicist. So I'll give example again the solar cell. Why I'm taking the solar cell example? Because it is the first and foremost material or the topic. It comes to the mind, oh, I'll do something with the energy, I need the energy and all. So that's what I'm giving the example. In solar cell, if you look at the literature, today's world, that what we are looking in the research articles like physicist, chemistry, material scientist, they try to explore the properties of the material, solar cell material. They get 44% what is called the efficiency. But if you go to your household, that solar cell you are buying and you are trying to utilize and explore in our household things, it is only in the new. When you are buying the new, they give the specification 18-20%, but after 1 year, 2 year, it drops to the 10 to 12%. So you can see the gap between the research and the modern, means what is called that your practical application, engineering products. And it is not that engineers are wrong or the scientists are wrong. It is nothing. In the laboratory, when we do some experiment and we try to explore, and we take the utmost care. But in the technological application, it is very difficult. That's why it is called the, you can say that the calibration constant, technological calibration constant, and that takes care. So similarly, in the magnetic materials, and mostly right now we are depending upon the most of the magnetic materials. I'll tell that only few. So one is means very you can say the world magnetic or like that Fe3O4, that was the first material naturally means find out in the Turkey that material to be the magnetic. It is the natural magnet. That was the ferrimagnetic. That way I am going to give the example on that only. That is the ferrimagnetic. Ferrites are mostly the ferrimagnetic, not the ferromagnetic. And but loosely people keep on writing the ferromagnetic. Please listen carefully. These ferrites, all ferrites are the ferrimagnetic, but we keep on writing the ferromagnetic because those ferromagnetic materials, they behave similar to the strong ferromagnetic materials. That's what we call these are the ferromagnetic materials. So the first invention was Fe3O4, but that the people try to synthesize in the laboratory and use in the practical use and all. But over the period, that ND-based, ND-Fe boron, that is the ND-West permanent magnet took the market because it has the highest magnetization, and mostly the engineering parameter is the BH maximum. And I will not go details. If anybody wants to understand, and you can ask me the question. The engineering parameter is the BH. B is the magnetic induction, H is the magnetic field, BH maximum. So that is the introduction, that the magnetic material, how we do. But for a physicist, we look for the MH loop, and always we look at what will be the coercivity, maximum magnetization, and all those parameters we give in the research. And then the people, engineering people, they find the BH maximum. So the engineering people, they get that BH maximum, and out of that parameter, so this is the gap, and we predict the MH magnetization and versus the H. And I will tell you that we don't look for the edging effect, and if there is a moisture and a dry place and all those things, we don't care. But we try to find out that what is the characterization of this MH. Then when we come to the technology, around 40 to 50% the efficiency will reduce. So that is the story of it, means difference between the technology and the laboratory research. So that's what we call always that technology is 50 to 100 years behind and to the laboratory research. So that I want to distinguish that while I will be talking about the magnetic applications, technological applications, don't feel that. And let me tell, I started the magnetic materials. I told the magamite, then the ND-West magnetic, and then if you look into that, people call it is the alkino or alnico, like that. These two things they use, that is the aluminum nickel cobalt or aluminum cobalt nickel. That is an alloy which is the rare earth free, because in the rare earth, you know that it is very costly and also not available in the earth crust. So that's what the people try to find out the different material. And also alkino that they are using, that, but alkino has a different problem in the sense it has a less coercivity, so that is you will not find very highly it is utilized. But the problem is that to make the alloy, and the people face the problem because you require the very sophisticated or very means environment, and industrial production is very, very difficult because you need the non-oxide environment, again heating and growing the phase are the lots of difficulty. Then the people find the alternative what we can do, then they from the magnemite, and then they find the granite and the orthoferrite and like that. But those their coercivity and the saturation magnetization is again less, and so that they could not bring it for the technological application. So finally they find the hexaferrite. It is very good for the practical application, and I don't know how many of you know that. And the people talk about that you are doing the oxide, it is only the laboratory, it is not. Already the companies have predicted that within few years they will be replace all the rare earth magnets by the hexaferrite. That is mostly they use the strontium hexaferrite or a combination of the barium strontium hexaferrite, which is a ferromagnetic, but it shows the very strong ferromagnetic behavior. Only thing is that it becomes a what is called the bulky material. When you go to the oxide, you require the large, because it's a magnetization and coercivity is less compared to your ND-West material. So that's what they are not able to replace immediately this ND-West material. So research is going on. So today we are going to see that in the different way you can modify the magnetic properties. But today we'll see that this composite, how it can modify the magnetic properties and how you can characterize, and mostly as a physics point of view, I'll make you the educated, or I'll make you the sound on this property, that is the composite. Because people do the doping and with the different annealing temperature, microstructure engineering, and so many methods are there to tune its magnetic property. So you may find in the literature, but today we are not going to discuss all these properties. We'll discuss that how you can tune the magnetic properties for the soft magnetic application as well as the hard magnetic application. So the two ferrites, and if you join together, how they will be affect to their magnetic properties. So it will be totally experimental observations, and the theory we are on the way. Already we have established on the way, and it is a separate theory, not the existing theory. And also today I'm going to tell that it is not an existing what is called the analysis to characterize the magnetic material and mostly the composite. It is the totally new way to approach the to extract the parameters. And you can see that nothing is new. It is that the observation, and it clicks to us that okay, we can find out the parameters in this way, in the better way we can present the material, that I will pass the message. So now let me summarize what we are going to discuss. We are not going to discuss all the properties. Only when you combine, it is not only ferrite, because I'll give the example of the ferrite. If you have a nano material distributed, or it is compacted, and you have a magnet with the nano grains, or you have the nano materials and you have combined and make a composite, how they will behave and how their image look will change, and that can be extended to for the technological application that we are going to discuss. Thank you for the patience, and I hope you understand what is the objective of today's talk, and we are going to understand this. The when you have the two materials, you make a composite, then we'll distinguish what is the nano composite, what is the composite, then we'll see that and how the property changes and how you can extract the parameter out of it and give the information to the technologists so that they can buy your means they can explore the utilization of your material. So that we are going to discuss. So already sir told my CV, and so these are my students, and 9 already got the PhD, and 1 is just waiting for the defense. We got the report at defense, and 10 students are doing the PhD under my supervision right now. And first and foremost, I will thanks to them, because they are my workhorse and who produce the data or who listen me, and they do their job, so that I have lots of data or the lots of observation which I can pass to you. Then thanks to the IED partner for supporting in the last 14 years, and my food as well as my laboratory expenditure and all those things to director, registrar, and they're very cordial, and they have given the support to carry out the research. And thanks to the organizer, and mostly this Nagarjuna PG Autonomous College of Science, Raipur, and give me the opportunity. And then the principal madam and Dr. Chobe, principal Dr. Chobe, and Dr. Ahila Udhya, that is a convener of the conference, and definitely the Bhargavi madam, and constantly in touch with me and organizing this, and without any trouble I could join, and other faculty members of the department as well as the college, and to give their time and effort to make it the success this conference, and it is very nice. And thanks to my collaborator and funding agency, and whenever I required, and they have helped me, and other students like postdoc and my MTech, MSc, and BTech students. And thank you very much, and the special thanks to the audience who is determined that to give some time to listen me what I'm going to pass the message. Thanks you very much. And I have this so many research topics, and we are working, and we have some patents and some PhD theses and all these things. But today we are only a limited and a very small part of my research output, that is the magnetic composite interaction of the magnetic materials in a composite, how they're interacting each other, how we can characterize that we are going to discuss. So I'll talk about this introduction to the composite. Listen carefully. I will talk about little physics, and very interesting that we have assumed an electron, and by assuming the electron, when we assume, we have given a mass to the electron and a charge to the electron and the spin to the electron. And how we have given? We have calibrated. We have calibrated the mass,
Sir?
charge. Yes.
Sir, I'm sorry I'm interrupting you, but slides, I think it's not changing, sir.
Is it?
We are on the first slide only.
No, the first slide I spent. Now, is it changed?
No, sir, it is the first only.
Oh, I see. Let me see.
No, yes, sir, changing. It is second now.
Second, but
More
it
thing,
is
sir.
not the slide.
Excuse me, Dr. Upadhyaya. One more thing, it is not a full screen.
No. It was full screen. In the full screen, it was not changing. So when I go to the come out from the slide slow, and it is in. Let me check. Wait. Is it changing?
No.
Is it changing?
No, sir. Second slide is there on the screen.
Not changing, huh?
Yes. Now it's
Is
sixth
it-
slide. Yeah. It's changing now.
Is it changing now? Let me present in this mode. Is it fine?
Okay.
Is it fine?
Yeah. Yes, sir.
Yeah. Let me go ahead. So what I was talking, thanks to the organizer and all, I'm not going to repeat. And this is my slide, and this is my current research topic. I told that I'll be talking about the interaction of the magnetic material. So, okay, fine. So now we'll be talking about the interaction between the composite, and you look at that, means I have drawn it. And if you also can think that exactly what we have done in our condensed matter or in the physics, so we have calibrated our observation, and we have gone to a smallest particle, you can say, the electron. That is our calibration. The electron is the fundamental, and it is we have also calibrated its mass, we have calibrated its charge, and we have calibrated its the spin. How we have calibrated, and I'm not going to tell you, please look at it very beautifully. We have calibrated. Don't think that somebody has come and given to us. We have observed something, then we have calibrated, like the meter scale. We have calibrated our time, we have calibrated our length, we have calibrated our mass. Similarly, we have calibrated our mass of an electron from the electrolysis experiment, and charge and the mass has been calibrated. Then the magnetization experiment, we have calibrated our spin of the electron. So all the property, very interestingly, all the properties can be explained. By considering or by understanding the charge distribution function, or mass distribution function, or the spin distribution function. What does it mean? How the charge is distributed on the material, how the your mass is distributed on the material, then the spin is distributed in the material. The charge distribution will be telling all about the electrical properties of the material, either the charge is bound or free. You know that if it is bound, then you will have the dielectric material. If it is free, you will have a your metallic behavior. And in the physics, only these two category can be happened, and other things are the special cases. Semiconductor, semi-metal, these are the special cases. So if the mass, your mass distribution will be decided, that what will be the strength of the material and all those things, and the spin distribution will be decided what will be the magnetic properties of the material. So that is the formulation, all about the formulation, very beautiful science and concise that we have done, and we know the means all the properties. And if you have any property, my request to the audience, I know that I can't pass all the messages, But if you have anything, please you recall how the electron density, charge density is distributed. No problem will come to understand the electrical properties of the material. Okay, there will be, we keep on talking about the grain boundary, grains and all those things. But while you are considering the grain boundary, just you recall, if it is a grain boundary, how the electron charge distribution is taking place. If you picturize it or if you model it, and immediately you can say that what you are observing, it is its behavior. You can explain in a proper way. So similarly to the mass of the electron, mass distribution of the electron and the spin distribution of the electron. We are not going to talk about the mass distribution and the charge distribution. We'll look into the spin distribution when the two materials are mixing. So already I talked to you that the magnetic hysteresis, if you look into that, the hard magnets and soft magnets, they are distinguished. Science is always particular. You look into that, the number. When the coercivity is more than 100 Westerd, we call it is a hard magnet. And when it is less than 10 Westerd, we call it is the soft. And in between, we can't distinguish it is a hard or soft. So we call it is a semi-hard magnets or the semi-soft magnets. So that's what, if you look into that, they have the different applications like hard magnets and the soft magnets. And so it has a very interesting thing. So I'm giving you the glimpse that the what is the behind it, and because some of you may not have in the magnetic background, and that's what I'm trying to make you that understand the basic, and easily we will finish that my observations. So if you look at the magnetization, and it looks for you that it is a smooth curve, and never we bother about in the bottom one, never we bother about the bottom one. Why? It is not a straight, it is not a proportional. So if you look into that, we write that it is the Rayleigh regime, that is basically the spin distribution are not uniform in that because of the defects in the crystal. You look at that. I told you that spin distributions are not uniform. It is due to the defects, because when you prepare the metal and to minimize the energy, always the defects will be there. That's what initially the defect has to be melt with the applied magnetic field. So that's what you get a Rayleigh regime. And when the domain and domain wall motion and all in between, but when the domain wall will form and domain wall will form, so that time you don't get the perfect magnetization because they will fluctuate. So that's what you get a Bragaussian effect. If you extend the curve, you will see the Bragaussian effect. If you don't extend, you will think that, oh, my curve is very smooth. So we call it the Bragaussian effect. So lots of physics is lying there, and in the old days we were not bothered about these things, but now physicists are looking the applications of these observations. They are doing the applications. So in each and every step they can have the different application. That's what we are bothered, and one has to understand. Then only we can develop the technology. And finally we get the magnetization rotation, that is nothing but your anisotropy inside the material. It will be always what we are talking about, the magnetocrystalline anisotropy of the material. So that magnetocrystalline anisotropy decides what will be your remnant magnetization and what will be your coercivity. You look at that, your domain wall motion and all, they are the intrinsic property, and as well as your magnetocrystalline anisotropy is the intrinsic property. Once your domain wall motion and all it is over, then your magnetocrystalline anisotropy decides exactly the application of the material. So this magnetocrystalline anisotropy can be modified. Listen carefully. Can be modified by the crystallographic grains, modification of the crystallographic grains and the crystallographic sites. Modification of the crystallographic grains and modification of the crystallographic site, you can modify the magnetocrystalline anisotropy. And this is a very interesting word. I don't have time to make you understand. Very interesting. So that will decide what will be your remnant magnetization and the coercivity. They will decide that. What will be the utilization of the material. That is the basic of it. So this is the magnetic domain. I will not go that movement because we are not going to that is the entirely physics. Now let us come back to the composite. That is the, if you have a single magnetic material, you have that property, that is nothing but your magnetic domains, and when you apply the field, they will start forming Bragaussian effect, then they will be melting the magnetic moments which is not in the direction of the magnetic field. So finally all the magnetic domains will be in one direction, and after that the magnetocrystalline anisotropy, what I talked about, this magnetization rotation, that is your magnetic anisotropy, and never the saturated will keep on increase because magnetocrystalline anisotropy never will be in one direction. Because I'll give you example. If you have a cubic crystal, you will have the 4 easy axes. 4 easy axes you will have, so you cannot apply magnetic field, and you can apply only in one direction, so other 3 will be hard. When you are applying the magnetic field in one easy axis, then other 3 will be the hard for that axis, so that is called the magnetic anisotropy. So you take any material, you will find the magnetic anisotropy, magnetic material, you will have the magnetic anisotropy, that will be create a coercivity and your remnant magnetization. So that's why we are lucky that we can utilize it. So that is all about if you have a single magnet. Now you comes back. So if you have the 2 magnets together comes to each other, now one will be magnetized in different way and the other will be magnetized in different way. That is the important, that to modify the magnetic characteristic. I repeat, so if you bring the 2 magnets or the 2 magnetic particle, you have a single magnet, where you have a 2 different kinds of the materials or 3 different kinds of the materials. So they come closer to each other, so they will decide that what will be your magnetization in the material. So when they comes to closer to each other, how much they can come, we call it is the correlation length. It is the most important parameter in case of the electronics as well as your magnetism everywhere. So the 2 materials or the 2 spins or the 2 charges, they have to come closer with the below the correlation length. We call, what is the correlation length? Correlation length is nothing but the significant, listen carefully, significant impact of the wave function of the charge or spin in the environment. That is called the correlation length. So it is in the order of nanometer, that is 10 nanometers. So that's what if you bring the 2 different magnetic materials below the 10 nanometer, they will start interacting each other, or the correlation length of the your electron spin is within the length of the other spin correlation length. So they will overlap and they will give you the different properties. So it is not very difficult to understand. We write so many things, but you look at the equation, your correlation length depends upon that when they overlap, that is the kxx0, you look into the equation, and when they start separating in angstrom, picometer or angstrom or nanometer, so the correlation length will be depend upon the L by lambda. L is the length, that is the how they are separating, and lambda is your means the first correlation, that means overlapping, and when they separate at least one wavelength of your correlation, means spin wave or the charge wave. This formula is valid for either electron charge or the spin correlation. Then it will be definitely either they will be in the linear or with an angle. So definitely you require a function to take care your what is called that if they are separated with an angle or 180 degree. So that will decide how the strength. That's all. This is a very simple formula. So now you will look into that, but I'm not going to theoretically to calculate. One can do it, but we will see the experimental observation how we can do it, and we will address it. So the nano composite, it is totally different from the composite. Listen carefully. So if you look at the composite, that means two or three materials, they combine and form a composite. Two or three material, they combine and form a composite. Then what is the nano composite? It is not that you bring the two nanomaterials and combine it, two nanomaterials, combine it, and you say that it is a nano composite. It is not. Listen carefully. I have told you the correlation link, that if you bring the two nanomaterials and combine it, you can't. So one nanomaterial has to come to the correlation length. That separation between these two in the composite has to be, first of all, they have to be within the correlation length. Another point is that they should not, and once there is one nanomaterial and its effect in its nearest neighbors of the other material should not affect to the another nanomaterial. Okay, so when I say, it will be very difficult for you to understand, so let me go. I'll tell you that what exactly. And so just for the confirm, are you in the slide number 22?
Yes, sir.
Yeah. So you look at that, the picture one, it is a simple material. In picture two, there are the two materials. Okay, so black one is one and the red one is other one. So you look into that, the second one, third one, the effect of black one on this is not affecting to the other black. They are not overlapping. But if you keep on increasing the concentration of the black material, what it happens that you look at that slowly, their effect. And for example, the sixth picture, VI, you look at that, they are the effect of one black nanomaterial is overlapping with the effect of the other one. So that time I cannot say that it is the nano composite, because its effect, it starts overlapping each other, so they become the composite. So that's what, if you look at the nano composite, you will have a material that we call it is the matrix. Then you will have the nanomaterial, which will have the means your filler. We call it is the filler. So here, if you look into that, the figure VII and II, VII and II, you look into that. In II, your red one is the matrix and the black one is your filler. But in case of VII, the black one is your matrix and red one is your filler. So you understand now what is the filler. Filler means when the filler particles are there, their one filler particle effect should not be overlap with the other filler particle effect. Then only I can call it is the nano composite, and particles should be in the nano again. So what will be the size of the nano filler? So one has to be again optimize it, because this nano size, when it goes to the filler, when it goes to the matrix of the your original material, so they should not create the, listen carefully, macro cracks. They should create the micro cracks. Micro cracks means micro world is below 10 to the power minus 6 meter. Very interesting science. I don't have time to pass the message, but if anybody wants to understand, I can tell. Science is very beautiful, very particular. Below 10 to the power minus 6. That is nothing but we call it is the quantum regime or the micro world, and where the black and white. And if they should create the micro cracks, not the macro cracks, that is the metallurgical grain or metallurgical observation. That is that the cracks which is observable and modifiable by the human being, and that will not be your composite and nothing. So they should create the micro cracks. So that's why the size is very important. If you look into the polymer and the ceramic composite and the means the optimized size will be of the ceramic will be around 20 nanometer. That is a separate story. But if you take the hard material, again their size will be depend upon that what kind of composite you are making. It is not straightforward. That's why the lots of research is involved. Lots of research is involved, and I can't pass again the message in this short talk. And if anybody interested, and you can ask me. So the composite is very fast. So in this, and we'll look at that, the particle size around 20 nanometer, 30 nanometer, because that is the optimized size to make a nano composite and see the properties properly. So I hope I make you understand. So that's why if you go to a composite, exactly you look at this composite and the nano composite, the property when you will start making the nano composite for 1%, 2%, 5%, 10%, you will get a peak value, and after that it is composite. So that's what we say, that the nano composite is that the ratio between the matrix and your filler should be less than 10%. Your filler should be less than 10% compared to the matrix, then we call it is the nano composite. And but if you look into the hard nano composites, and their percentage is around below 5%, but if you go to the polymer, it is sometimes the property increase up to 10%. So because polymers are soft, easily they can incorporate the particle, ceramic particle. So that's what it is, the composite and nano composite we distinguish. Now let us go immediately that you choose the two magnetic material and combine, and how they will behave in different way. So these are the examples. This is the composites we have picked up, and these are the known compounds, okay, known materials, and people are working and all. You may think that nothing is new and all. You don't think that the research is always the advance of the material, but you have to observe properly that what the new things you can do and you can extract. So we have taken, you look into that to understand exactly the interaction between them, and we have taken the very, very weak magnet like BTO. If you reduce the size, and due to the surface uncompensated spin, they show a magnetism, very small magnetism. BHF is very hard, and CFO is also a very hard, very magnetic. Then BLFO is a very, very means you can say the weak ferromagnet, as well as BTO is the weak ferromagnet in the nano. So combining that, how it is happening. And if you look into the NG, nickel zinc ferrite is a soft, BHF is a hard, that also we looked at. And again, nickel oxide is a anti-ferromagnetic, no magnetic, ferromagnetic, but CFO is a very, very hard, very magnetic, and it is not the limited to this. And I picked up that to look that with the different magnetic properties, when they come closer to each other, are they affecting to the magnetic parameters, and which can be utilized for the modern technology. So that was the means our basic idea in the magnetism. So we took the different combinations of the known and well-established magnetic materials, and to find out oxide materials, to find out. And already I told you that non-oxides are difficult to handle. That's what the people are looking. And if you look the statement, next slide I will go. If you look at the statement, the Fujifilm and the Japanese are way ahead of to the rest of the world, and they go very fast. And you may not like their product and all consumer product, but if you look at that, without Japanese, and there will be no technology, and you require their help. So those Fujifilm Corporation, they have challenged that by very, very soon they will replace all the alloys, because they are difficult to produce, by the hexaferrite, and to make the memory chips. That is nothing but your magnetic recording media and whatever the magnetic applications they are trying. And also the IBM is supporting that they will be doing all those ferrite magnetic materials. You can see the opportunity. That's what, if you look at that, after their prediction, and there were the very interesting properties. Fine. So if you look at the literature, the cobalt ferrite and barium hexaferrite, I will not go details. Please look at that. These are the ferrimagnetic, and they are very, they have the interesting properties. So that is the cobalt ferrite and the barium hexaferrite. And they have the very interesting property that they have the magnetic, means hard magnetic parameters at the room temperature, very high coercivity, and etc., etc. So that is the, and also the nickel zinc ferrite. If you look at that, means when you go to the nickel zinc ferrite, and that time you will find that they have the soft magnetic properties. Fine. So in the barium titanium oxide, when you reduce the size, they will become the nanomaterials and they will show the magnetism. I told you that in this. So in the barium means your bismuth ferrite, if you look at that, these are the antiferromagnetic, but their antiferromagnetic at the cycloid structure. So the structure length is 60 nanometer. If you reduce the size, then you will get a very interesting magnetic properties. So these are the properties we look and pick up the material. And nickel oxide is a totally anti-ferromagnetic material. So that's what we pick up this. Now we'll be looking that when you combine this, and first of all, I told that they have to exist independently. They should exist independently to show, and they should come to a correlation length, and so that they can show the different property. That was the aim, and that I'm trying to give you the message. You look into that BHF nickel zinc ferrite, and if you are a young researcher, you can say that in first you have to go for the XRT and look into that. Are the structure is existing? If you look at that independent, but if again you have to go to the XRD of the combining these two, and both the structure has to be present that you can observe. So that I think it will be difficult, and we did the default and to look into that exactly what has happened, and these are the parameters we obtained, and we confirm that they are independently existing at the from the X-ray diffraction. But you know that it is the first and foremost experiment, but you can't confirm. There may be the solid solution. That's what we went for the TM measurement to look that really are they sitting together and doing. So we went to the HRTM, and you can find and the two structures, because of their compatibility, they are sitting together and with the close, and that is in the atomic order, and they are close to each other. So that says that it is the basically they are in the within the correlation length. XRD and TM, they support the data. And the real thing is that when you look at the MH loop, they are not the similar to each other. They change their shape. You look at that, the when you change the percentage, and there is the squeezing, and you look at the third line, there is the squeezing of the loop at the zero applied field. So that means that also another way indirectly says that these two material, they have not chemically they are not reacted sitting separately, because one is behaving a tiny magnet, another is tiny magnet. They are affecting to each other. If they react a single material, you should get a single loop, but they are biasing each other independently. They are existing. So once we assume and understand that they are independently sitting, but now you have to extract the parameter and understand their interaction by this. So we look at the literature, but if you look at the literature, you will find also the similar behavior. But what they talk about that, they say that it is a, in the literature, they say that it is a spring magnet. If you look into the bottom picture, they demonstrate it is a spring magnet. But to analyze it, they do lots of tedious experiment by increasing the magnetic field, decreasing magnetic field. Really, it takes around a week for a sample to look at the relaxation and tell that it is the spring magnet. We look at the literature, but you cannot do always the experiment for the technology and do it. And you need a easy way to tell that they have the interaction, they have coercivity, and etc. So these are the literature existing and explanation. Then we look at it, and you look at this curve, and you will not find commonly this curve, and this has been extracted from, and right now I am in the 31 slide, and these are the hysteresis loop. From this loop you can derive these curves. How you will derive? And this is the loop width versus magnetization. Let me tell little bit, as it is not very common, and let me tell, and you just pick up any hysteresis loop. Suppose let us talk about the A, and what it will be happening, you take that there will be the magnetization. So in each magnetization, if you draw a line. Suppose let me put it and you will understand. If I put a dry line like this, you will get a magnetization value here. Okay, and just I'll put another point, and you will get a magnetization value here. Then and I'm moving and a H value here. So what I'm talking about, and this line will decide the magnetization here by basically remnant magnetization. And if I draw a line here, this will give me the H value, and this will give me the H value, and this will also give me the H value, minus H and plus H. Then I can calculate what is my delta H. That's what we take the modulus, delta H modulus. You will get a difference of the field, and you will get the magnetization of each magnetization. You will have a delta H. So once you get this, listen carefully, and you plot it, delta H versus M, you will find that if it is a single domain or single type of magnetic material, then you will get a very smooth curve. And the first one, again, I'm talking about this. Okay, I'll put this. And the first one, you look into that, and this one is your single type of material, that is nothing but it is a nickel zinc ferrite. And in the bottom one also you look, I'll just highlight and remove the bottom one, you look, and this bottom one also the BHF. So they are the single material, and when you mix it, you look at that, and some hysteresis loop also you are unable to observe this kind of, is there an interaction when there is a small amount like 92 of BHF and in the 0.08 of the nickel zinc ferrite. And I'm talking about this, the second curve, then what you will find that you look into that, there are the small interaction. But when there is a very high interaction, for example, if you look into the 50-50, you look at that, there is a two types of the Gaussian. So that to tell you that what is the strength of the magnetization. If anybody is interested, you can look at our paper, how we have told that the strength of the interaction can be predicted from this curve. If there is the high strength, then you will get very loose curve, and it will be there. And also we have seen, and don't think that this is only that when you mix it, you just take the BHF and BHF of different size, or nickel zinc ferrite of the different size. Also the similar curve you will be observed if they are the particle distribution are different, because particle with the particle size, you know that in the nanometer order, if you change the particle, then the materials will have the different property, different magnetic property. So if you bring, also you will get the same thing. I will tell you that the people in the 1970 or before 2000, they say that this is the amorphous nature of the magnetic material. But you look at that, the amorphous is, there is no perfect amorphous. When you say the perfect amorphous, it is only the liquid. And if it is a solid, definitely there will be the ordering, either 1 or 2 or 3. So in a certain level, and X-ray cannot observe their ordering, we call it is X-ray amorphous. So those materials are nothing but the tiny magnets and combined. So that's why the people are observing the similar type of squeezing of the hysteresis for the amorphous material. So we conclude that this explanation or this observation can also extend to the amorphous material. Also, it can be extended to the thin film, and right now we are working on the thin film, and maybe within a few months you will find the paper. The same concept is applied to the thin film and explained its property. So this is the means concept. Then this I told you that if you look at that, you will find that depending upon the strength of the interaction, and you will have the delta H and M versus curve will be different. So this concept we proved. I told you that with the different material, and this is the best. Barium hexaferrite is a hard ferrimagnetic material, but in literature always you look that people write it the ferromagnetic, but its ordering is a ferrimagnetic. So nickel zinc ferrite is a soft ferromagnetic material and we combine, we look at it, then we get the property. But if you look into the magnetic properties and we predict that in the initially I told, and you look at that when in the nano composite, you look into that the property has highest, then when you go to the composite and it will be in the different way. And if you look at that, I'll just highlight, and this one and your this region, both are the nano composite region where the properties are highest, and one is in the other way. One is the matrix, another is the filler. And for 0.1 and means in the left side, and your BHF is the matrix and nickel zinc ferrite is filler, and in the other side, and your nickel zinc ferrite is the filler, and barium hexaferrite is the your barium hexaferrite is the filler, and nickel zinc ferrite is the matrix. Already I told you that the percentage of highest one depends upon the characteristic of the filler and matrix. So that's what you have to careful that when you are explaining or you are looking to the composite materials, not only this magnetic, but also if you are working in the composite dielectrics or it's a thermal properties and etc., always you will observe the similar curve, which also we reproduce experimentally what the theoretically explained in the nickel zinc ferrite and the BHF. So I'll not tell, it is fine, the summary already we told. Then we go for the another, that BTO, which has the very less magnetization, and BHF, it is a hard ferromagnetic. Then also we demonstrate, and BTO, you look into this first curve, BTO was the diamagnetic material, this one diamagnetic material, but when we ball milled and make it the smaller size, around 30 nanometer, it became a ferromagnetic. So then we mix it with the BHF and do it, and we find, and from the curve you may not see that where is the squeezing and all, but the method I propose, you look in that, if you separate, you will find the small squeezing, and which is very difficult to analyze from the raw data. But if you go to the plotting of the method I told, delta is versus AM, you will find that there are the interaction. This is another proof. So all the TM and all, it is there, and I'm not going, time is short. So then the BTO and CFO also, again we observe that in the BTO, although very small magnetic moment, but when they come closer, you can look at that, and they will have the very strong interaction in the cobalt ferrite and BTO. Now let us go back and look at that in the other one. We find the BHF and BTO, but nickel zinc ferrite and BTO, they have a better interaction. Why? BTO is a perovskite structure, cobalt ferrite is a cubic structure. So in the better way, they can come closer to each other and give you a better interaction. You look at that in the science, how it is beautiful, and the observation. And their structure is close to each other. But in the BHF is a hexagonal structure. So a perovskite, it will not be very easy to, in the surface, to combine each other. That's why they will be always a little far away. So that's why their interaction is less. Although BHF is a very strong magnet, but their interaction is very less, because BTO is not influencing to the BHF. That's what you are getting very, very little interaction. But in case of the cobalt ferrite, is the structure is compatible, so they come closer to each other, and you get the very beautiful interaction between them, or the maximum interaction with them. So you can modify that property and you can get the property. So again, I repeat, BHF, BTO is the different structure, means it is not very close to the BHF. BHF is hexagonal, BTO is the perovskite, it is close to the cubic. So orthorhombic, you can say orthorhombic, tetragonal, and different structure can take the BTO. So but they are close to the cubic structure. So if you have a cubic material, they can come closer. You look at that, my thought of the science, and which is easily it can be observable from the experiment. So they are not coming very close. That's why their effect interaction is less. But still, I can say that they are within the correlation length. Correlation length, because the interaction is observable. So then if you go to the nickel oxide and CFO, nickel oxide is an antiferromagnetic, very interesting. It is totally antiferromagnetic. Magnetization is zero, close to zero. And cobalt ferrite is a hard ferromagnetic material. When we mix it, So what will happen? And when you mix, so one antiferromagnetic, another ferromagnetic, interaction is there. That is, we observe, it is fine. Again, nickel oxide and cobalt ferrite, their crystal structure is close to each other. That's why they can come closer to each other and give you a better interaction. But the question is that nickel ferrite is having the less magnetic moment. But you'll be surprised to know the cobalt ferrite original magnetization increases when you put the nickel oxide. Why it happens? Because of this interaction. They also increase the saturation magnetization. This is interesting that you can increase the saturation magnetization of the cobalt ferrite by adding a antiferromagnetic material, so that you can have a better way to utilize the cobalt ferrite and this material. So that's what again, I think it will be my last part of the bismuth ferrite, which is very, very less magnetic moment. There also we break the antiferromagnetic, that is the cycloid structure, so that you can get a ferromagnetic material. So that ferromagnetic material, ferrimagnetic, not ferromagnetic, ferrimagnetic material, then we interact with again small magnetic moment of the barium titanate, and we see that. And again, you look into that, the interaction, although their magnetic moment is less, but the interaction is very high. Why it happens? All of us know that. And if you don't know, and this is the information, BFO and BTO are the similar structure, and CFO is spinel but cubic. But here they are both are the perovskite structure, and that structure are very close to each other. Okay, sometimes they form also the same structure. That's where they can come very close. You look into the delta H versus M plot, you will see that whatever the curve we see, this is the most interesting and the complete interaction, because that structure is close to each other. So you look at the science is how beautifully, and when you look at the structure, when they are very compatible, they can come closer and closer and bias to each other and modify their magnetic properties, so that you can tune the magnetic properties for the technological applications. And then that this is the magnetic properties of BLFO and BLFO, not BFO. BLFO, it is a different of the BLF BTO. They are also the strong interaction, and you get it. So, so what is the take-home message? Magnetic interaction between the two phases in composite is important factor to modify magnetic properties. The failure percentage of nanomaterials is around 10% or less than 10% compared to matrix element in the nanocomposite. The nanocomposites of barium hexaferrite, cobalt ferrite, nickel zinc ferrite, barium titanate can be prepared by the high energy planetary ball mill by bringing their tiny magnets with the below the correlation length, spin correlation length, basically spin correlation length. Chemical interaction can be avoided by keeping the low RPM and etc. You can control and you can avoid the chemical reaction between these materials and tune the magnetic properties and very beautifully, and you can analyze. And analysis of perceived field at different magnetization suggests the magnetic interaction between magnetic phases of BTO and BHF and nickel zinc ferrite. Also you can look. So that is our observation, that you can take a message, and you can also, if you are trying to do something in the magnetism, and you can look at how you can make the composite and create the different kinds of the magnetic material for the technological application. Then the saturation magnetization and magnetocrystalline anisotropy increases with increase in BHF content in the nanocomposite. What we see in all of the cases, we see that when you increase the BHF, it is happened because it is hexagonal, and the other material we took, it is there orthorhombic or tetragonal and or rhomboidal. That's what the anisotropy at the surface increases. So the most important is that it is the new information, that is the loop width versus magnetization curve derived from MH hysteresis loop, magnetic loop, reveals the interaction between the different magnetic composites. Also, this analysis can be extended to the amorphous material, amorphous magnetic material, or thin films of the heterostructure, thin films of the heterostructures. Thank you very much. I hope I finished within the time. I started around 12:20. Thank you very much for giving the opportunity, and thanks to the audience for giving their patience and listen me. and generally in these type of talks and speaker goes fast. So that's why I don't know how much message I passed, but I will be happy to address if you have any query. Hello.
Yeah, thank you, Professor, for completing in time. It was a very organized presentation. As we have few minutes, we can take some questions. If any query, you can ask audience. If you have any query.
Sir, this is Dr. Anjali Avadia, convener of this conference, and this was a very nice talk, and actually I had a question. So may I ask if you allow me?
Yes, madam, I'm hearing you. Please, please.
Sir, so one of my scholars was working on simulation of zinc oxide structure, and she made two structures. One was a buckyball kind of circular structure of 24 atoms, and another one was a zinc oxide hexagonal structure. And to our utter surprise, we got magnetism in the buckyball structure, but not in hexagonal. So I was asking her to search about how does structure of a material affects the magnetic property, and can we initiate the magnetism just by changing the structure. So your talk covered a lot of my queries actually. So would you suggest how to go further and correlate this? Do we have any theoretical background or theoretical calculations to correlate the magnetism and the structure, as you said, magnetocrystalline and isotropy and crystallographic and isotropy and all. So we would like to work on this theoretically also. So please suggest if yes.
So madam, if you change the structure, definitely the magnetic properties can change, as well as if the one can be non-magnetic, another can be magnetic. For example, and actually I did not, and if I get the chance, I'll tell. And actually, I'm a hardcore experimentalist. Right now, we are developing the theory entirely from the scratch. One of my student is not doing at all the experiment, is just trying to develop the theory from the scratch. So already we have formulated, and as it has not been published, and I'm not this, and also time is not there. What I'm talking about that right now, and we have a paper on PRA, physical review applied, and there we have shown that when you have the crystal structure transition, then the magnetic transition also takes place. That is, it is very difficult to get that transition, like the magnetic transition with the crystal structure transition. It is in the alloy, not in the oxide. But what you said, it is possible. 100% it is possible. You have not observed any what is called the absurd result. It is possible when the different structure, because I told you that magnetocrystalline anisotropy, that decides that what will be the magnetism in the material. So that means easy axis. So my hints will be, or my thought, it is that you are getting the hexagonal and another is the buckyball. So in that case, you have to just look that in your material, as you are in theory, you are working, and in the structure, you look that what are the easy axis. If you can catch in the both the cases, in the both the structure, what are the easy axis of the magnetization, that will give you the answer. Okay, could I explain you that?
Yes,
You just
sir,
look
definitely.
at the easy axis in your hexagonal structure and easy axis in your buckyball. So that will tell. And in the buckyball, what I understand, buckyball, you are getting the magnetism. It could be because of the surface magnetism. Magnetism. This is the two things immediately coming to my mind, that due to that you are getting the difference.
Okay, sir. We'll definitely look for that answers. And thank you so much for explaining in such a detail. If we can get the reference of your paper, which is already published actually in physical review, then it will be wonderful.
Yeah, definitely, madam. I'll share with you. That is the basically first order magnetic transition. When structures are always the first order transition, but magnetic is second order. But in case of the coupling both of them, always you will get a first order magnetic transition. So that is that.
Thank you.
It is that,
Thank you
that
so much.
paper is on magnetocaloric effect mostly. So
Okay. Okay. So we'll get that and we'll be in touch. Thank you. Thank you so much for the presence.
Any other question? We have 1 minute. 1 minute left. So if there is no more questions, let us thanks Dr. Manoranjan for his nice presentation. And now I over the session to Bhargavi.
Thank you, Upadhyay sir. I thank both the two speakers, Panigrahi sir and Manoranjan Kar sir, for accepting our request. Thank you so much, sir. You always accept my request, and we patiently listen. And another time we are again ready to listen another of your talks, sir. Thank you so much.
Yeah, I'll be happy to give him the polymer, and it will be totally, and you may think that it is only the magnetism and polymer who have done something interesting.
Yes,
That actually means nowadays when corona over, very difficult to confine yourself. And again today, just after this talk, and I'll have something, and I have to go out, and I have some assignment, and again I'll come back tomorrow again, and the next day I have to visit. So that's what this is very difficult. Corona was better. Corona thing was better because we are not moving. Thank you, madam. Thank you very much. Thanks to audience once again, because they listen. That's what you can arrange, and I can speak. Thank you very much.
Thank you, sir. Thank you so much.
Okay, thank you very much. Okay. I'm leaving. Thank you.
Okay, sir. Okay, thank you, Upadhyay sir, for spending time with us, sir. Thank you so much.
Thanks, Bhargavi, and thanks to the organizing committee for giving me this opportunity. Thank you very much.
Okay.
Thank you, sir. Thank you, sir. Upadhyay, sir.
So we will start the second technical session at 2. So participants are requested to join sharply at 2, please, so that we can conclude our sessions on time. Adhya madam, can I leave for some time? Yes, sir.
Certainly, sharp at 2. And I request all the participants to join us again for, there will be very interesting talk of Dr. Alka Garg on polymer materials. And after that invited talk, we will have oral presentations. So I request all the participants who are scheduled to present their work should be there, ready with the presentation, and expect to see all at 2 o'clock. Thank you.
Verma sir. Hello, ML Verma sir.
Yes, yes, I am here.
Sir.
My voice is clear?
Yes, sir. Yes, sir. Madam, sir, shall we have to wait for Anjali madam, or if you want, you can start, sir.
So we should wait for 5 more minutes.
Yes, sir. Yes, sir.
Okay.
Because the invite, our resource person has joined.
Okay, so you will give the details of our invited speaker first, because I don't have the details of speaker ma'am. It is speaker ma'am. Yeah.
I will.
Okay, so you have to introduce ma'am and welcome, and then just we will start. Okay.
ये 2-7 हो गए हैं ऑलरेडी। सर मैडम हैज ज्वाइन, अवधिया मैडम ने ज्वाइन कर लिया।
For the delay, actually, I was in some schedule. So I welcome Garg ma'am and ML Verma sir, and thank you so much for joining us. And Bhargavi, please take over now as per our schedule.
Good afternoon, everyone. We are in the second technical session of our 2 days national seminar on advanced materials and characterizations 2022. In this technical session, there is one invited talk which will be delivered by Dr. Alka Garg madam. And after this invited talk, we have some oral talks. So all the participants who are presenting their oral talks are requested to ready with their presentations so that we may not have any mess. And before handing over this session to our chairperson, who is Dr. ML Verma, sir, I would like to introduce our invited speaker. Our invited speaker for this session is Professor Alka Garg. She is Associate Professor at Department of Physics, Gargi College, University of Delhi. She has awarded the doctorate degree from Delhi University in the field of X-ray crystallography. She has been conferred with Certificate of Recognition in Appreciation of completing 25 years of dedicated service in the institution in 2020. She has done postdoctorate from Delhi University in the field of high energy radiation detection. Awarded as a best performing teacher award in 2020, instituted by Government of NCT of Delhi. She has been awarded a project designing and study of lightweight portable polymer-based bismuth triiodide composite radiation detector for medical application by IUAC in 2021. She has also awarded with innovation project funded from University of Delhi in 2012 and 13. She is selected from among the undergraduate and postgraduate teachers from all over India to promote research-based learning in universities of India, and trained almost 200 teachers in various universities of India till the date to promote RBPT. This mega project is funded by MHRD and DST in collaboration with ICER Pune. She is supervising PhD students in the field of high energy detection system, and she is member of Indian Association of Physics Teachers and International and National Association of Crystallographers. She is also an active member of Eco Club Gargi College and has organized many events along with other Eco Club members to sensitize students among the environmental awareness and environmental protection. With this brief introduction, may I now request Madam, and I hand over this session to ML Verma sir. Sir, please.
Okay, thank you, ma'am. And now I invite Dr. Alka Garg for this invited talk. And the title of her invited talk is Polymer Composite of Metals, Metal Iodide for Direct X-ray Detection. So, Madam, please welcome and share your experience.
Thank you very much. Thank you very much, Dr. Bhargavi and Dr. Mohan Verma, for giving this introduction about me. And I am really thankful to organizers for giving me this chance to present my work in this talk. And though I have worked in the X-ray crystallography, but this is the area I was passionate about and working on it for the last, I'm working on it since 2018 on detecting high energy radiations. So I am going to present a talk on how these what modification bring the addition of polymer to metal iodides for bringing best detector structure. So I am presenting my screen. I think all of you can see my screen.
Yes, ma'am.
Yes. So the title of my talk is Polymer Composite of Metal Iodides for Direct X-ray Detection. And since mine is a UG college, so it's an undergraduate college, so we don't have much of a research facility. So this work has been done under the collaboration with a professor from IGDTU, that is Indira Gandhi, Delhi Technical University for Women, where we have all the three like UG, PG and PhD students being enrolled. Now, before I start my talk, I would like to say that these polymer composite of metal iodides are used for detecting the high energy radiations. Though here I would be only talking about the X-ray detection, they are very good. They are very good for even for detecting the gamma radiations. Okay. And we all know that X-rays are basically broadly divided into two ranges: the soft X-rays and the hard X-rays. So soft X-rays are the one which lie between the range of say 100 electron volt to 50 kilo electron volt, and beyond 50 kilo electron volt we call them as a hard X-rays. Okay, hard X-rays, that means above 50 kilo electron volt up to high mega electron volt, they have high penetration depth. So their utilization is mainly in the industry. For the medical purpose, we always intend to use the low energy X-rays, so that the harm and also the dose which is being given to the patient is less, and we try to synthesize or innovate our material in such a way that we get better resolution, good contrast. So these are the things we want from the detector. Okay, and the use of low energy X-rays, they have a predominant role in the medical industries. Now, why polymer composite and why not the compound semiconductors? Like I should say that silicon and germanium are the one which are being used. Okay, but they have some inherent problem associated with it. We cannot tune their band gaps because of the limitations associated with the use of these two major semiconductors. So the question arises: to tune the band gaps, we need to build compound semiconductors. Compound semiconductors are like the simple examples of cadmium telluride, or when the different dopants have been used, like zinc has been used within the cadmium telluride to make it a cadmium zinc telluride for better resolution, for better sensitivity, and for better environmental stability. And also these metal iodide which I am talking about, apart from the cadmium telluride, what often are being used are the lead iodide, zinc, mercury iodide, and bismuth iodide. Lead iodide and cadmium iodide detectors are very common, but a toxicity is associated with them. So BI3, I suppose, and through the literature survey also, we had seen that the addition of Bi to the polymer composite, or addition of bismuth iodide to the polymers, different polymers give me a better structure as compared to lead iodide and cadmium iodide. So this is how we started to build the polymer composite of metal iodides. Before we start with the proper, giving you the results of what we had obtained, I should tell you that there are two kinds of actually detectors: the direct and the indirect detectors. Okay, indirect detectors are the one. Direct detectors, indirect detectors are the one which are scintillators based. Scintillator based means which converts the absorbed high energy into visible light, and this visible light is used to produce a current pulse, and by analyzing the current pulse we could able to get the energy which is being with which our material is being irradiated. And the direct detectors are the one where we don't need a very high electronic systems like PMT, or other electronic system. So the direct detectors are the one which are used to photoconductive materials. And on irradiation, what happens, since for evolution of an electron hole pair only a small amount of energy is needed of the order of 3 electron volt. So when these direct in a direct detector, when these photoconductive materials are irradiated with the high energy, maybe X-ray beam or a gamma beam, so the number of electron hole pairs created with one photon of X-ray is huge in number within a material. So the question arises, what kind of material I should have? Okay, the material where the density is high, where the materials show high absorption coefficient. Okay, so on this basis we choose a material and then we try to build the direct detectors. So my work is on the direct detectors. So what are indirect? They have small efficiency for energy transfer, whereas the direct detectors, they have large efficiency for energy transfer, because the band gap is, we know, it's very small for the semiconductor material. Okay, in the indirect detector, spatial resolution is something which is guided by FWHM. Okay, that is limited by the light spreading. Okay, whereas in case of a direct detector, I will show you the result also, it has good spatial resolution. Okay, these are the advantages which are associated with the direct detectors. Okay, and other major advantages which are associated with the direct detectors are their quantum efficiency is high. That means quantum efficiency is high. That means one photon, when one photon, if I say, irradiated or is put on a sample, then it leads to large number of electrons. So the energy resolution is high. So because of this, what happens, we can work on a low dose operations, which is what our intention is for the medical industry. If we can easily see the organ or something or some material with a low dose, it would be nice for the patient, even it is energy effective then. And also the high direct detectors have high image quality and resolution. They show high sensitivity with low dark current. Dark current is the one, it is also known as the thermal current. It is, we can say, it is the one which is actually degrading the performance of a direct detector. So in order to make a low direct current, or we can say the current which I am getting in my material when the beam is not being held, or when the material is not being irradiated with the X-ray beam or the high energy beam. Also, since I am making use of, I'm blending some kind of a polymer to it to have the high sensitivity and high quantum efficiency, so they are made, we can make them light. Okay, so this is what the advantage of direct detectors are, and they can be built with simple lab techniques. That means we don't need PLDs, we don't need high apparatus like MPE apparatus to build these detectors. With simple lab equipments, we can devise the direct detectors, and cost is of course then less, and they require almost no space to work on. So these are the advantages associated with the direct detectors. Now, what material should I choose? I gave you the example initially, like the cadmium zinc telluride or the metal iodides, basically lead iodide, cadmium iodide. My work is on bismuth iodide because I wanted to choose a less toxic compound. Okay. Now, what properties should have? First, I told you it should have a high density. So the number of electron holes which are created are high. Okay. Also, they should have low charge pair energy. That means large number of electron hole pairs are created, so the energy resolution would be more. Good transport properties is something associated with the mu tau. We all know mu is the mobility and tau is a lifetime. So higher the mu tau of my material, good it would be like if the electron hole pair is being created at any point on my detector, that can be easily flowed to the electrode and responsible for my current pulse, right? So the good transport properties are the essential. So we have to look into the mu, that is the absorption mu, which is called the mobility. Okay, all these parameters are guided by the drift length and also the length of the detectors. So if you if you go into the detail, so this mu tau is actually directly proportional to the drift length and inversely proportional to the length of my detector. So this put a restriction on the size of my detector. Okay, and also the material should have low dark current, which is possible only if my material has high resistivity. Okay, so but semiconductor with high resistivity, it's this combination is we have to work on it. So that is how we intend to use both, or we intended to blend polymer which has a high resistivity of the order of 10 to the power 15 to 10 to the power 18 into our semiconductors, which show a better which show a better conductivity. Okay, and since the manufacturing cost is low, so they become cost effective, and we can work on different kinds or different kinds of electrodes. So we can try different modes in order to get the maximum quantum efficiency, right? Now polymer, we know these are the properties which are associated with the polymers. They have high resistivity, they show good mechanical properties, high stability. Synthesis is very less. So what we had done, we tried to blend both of them to make a composite. Okay, and the chosen material was bismuth iodide, and we added the polymer in different proportions in bismuth iodide. We also tried different kinds of polymer, like we worked on the polystyrene, we worked on the PMMA, then we intend to work on other polymers also in order to see what is the quantum efficiency or what is the sensitivity of my direct detector, and also how much is my dark current or the thermal current associated with the polymer. Okay, all of you should know that the absorption coefficient of any material is proportional to the fourth power of the atomic number. So higher the atomic number, the more would be the absorption of that, more would be the absorption of my incident energy. Okay, so that means I want to use a material which has high Z. So bismuth iodide being an ideal material which has got a high atomic number. Okay, since Bi3 is a fragile and also soft semiconductor, and since it is a hexagonal in nature, so what do you mean by it consists of like it's like IBI, and then two neighboring I bonds are linked together through a van der Waals force. And we know through the principle of microscopic growth that all the voids, all the vacancies, they tend to flow towards the bond where the bonding is weak. Okay, so these interlayer of iodine bond makes my sample susceptible to noise. Okay, and that is why the polymer having high resistivities are being added into it, so that my material or the semiconductor material is embedded within the matrix of the polymer. And this we had seen also through the SEM analysis, that layers of polymers had been seen, and the particles of Bi3 are like sparsely or uniformly embedded within the matrix of of the polymers. Now this to overcome the problems which are associated with the bismuth iodide, this we have blended with the polymer. Okay, and which forms a nano composite matrix. Now, what is the nano composite leads to strong reduction of charge carrier recombination and increased charge carrier mobility due to strong impact on the semiconductor morphology. What happens is these bismuth iodide and polymer composite, when they are blended together through a technique, what happens is Bi3 are embedded in matrix in such a way that they form a tips, and due to the high electric field concentration at the tips of the Bi3, what happens, the charge collection become a easy mechanism. So it's like a hopping of the charge carriers being takes place through these tips of Bi3. So what happens is when the X-rays are being irradiated on a sample, the large number of electron hole pairs which has been created, instead of going into the II layer or the interlayer of my bismuth iodide material, they tend to move towards the electrodes. Okay, why? Because addition of polymer into the bismuth iodide leads to the mobility, charge carrier mobility being high. Okay, so the chain of polymer makes cross-linking with these vacancies of high Z semiconductor. Okay, so due to this excellent connection between the polymer and semiconductor, the efficiency of, I have seen the enhancement in the efficiency of my direct detector materials. Now, I'm quoting you a few results which we have obtained in our research lab, and they are well published. Now, what we had seen that if I make a composite of polystyrene and bismuth iodide of different combinations, we started with 30-40, we started with 30-70, 40-60, then 50-50, and then 60-40. That means we are increasing the concentration of polystyrene and bismuth iodide. So through the result, we had seen what we had done. First, we had taken the XRD just to see how the addition of polystyrene is making changes into the structural configuration. As such, since bismuth triiodide is there as a particle and embedded in the polycrystalline material, so we have seen that all the peaks, all the XRD peaks corresponding to bismuth triiodide are well shown in the XRD pattern. And you can see from the peaks that you have 003 plane, you have 006 plane, 009 and 0110 plane. These are the planes which corresponding to the layers which are perpendicular to the substrate. Okay, these are the plane which are corresponding to 00L planes. Okay, that means somehow because of the layering structure of bismuth iodide, I am getting like a C-axis parallel to my substrate. C-axis perpendicular to my substrate. That is why I am getting high 003, high 00N. And as we are increasing the concentration of Bi3, I should see that at S4 is the one where there is less Bi3 and more PSA. More PS. So you had seen that material is going from the crystalline nature to the amorphous nature. And if you look at the sample through the analysis, we found that when my composition is 50-50, that is when the composition is 50-50 weight wise, then I had seen the maximum SNR I have achieved. What is SNR? It is the signal to noise ratio. And this since the X-ray of energy 30 kiloelectron volt had been used, and the bias voltage is the one. This is the disadvantage associated with the direct detectors, that we need to bias it in order to attract these charge carriers or the electron hole pairs which are being created at any point within the detector. So we need to apply a external bias, reverse bias of 50 volt in order to catch these charge carriers which has been embedded or which has been produced on irradiation, right? And what we had seen is this SNR is around 70 at 50 volt. And also if you look at the rise time and the fall time, It's through the calculation we found out this comes out to be around 0.5 second. And this is, if you compare it with the commercially available detectors, we had seen that for them the rise time and the fall time, they were lying in the order of seconds. So that means the work we have started, that is going in the right direction. Okay. And also the leakage current, if you look at the dark current or the leakage current, another term is the thermal current. Of course, as you increase the bias, that means as we are increasing the bias from 0 to 200 volt, I am seeing that my leakage current is increasing. This is quite possible. This is quite possible, and we have to decrease it. Ultimately, our aim is to optimize our applied bias and optimize my characteristics in such a way that I get low leakage current and high SNR. It's nothing but SNR is a signal to noise ratio, which is a ratio between the photocurrent, and it is a difference of the photocurrent and the dark current. Photocurrent is the one if you get a highest. Okay, you can see the highest current which you get when the sample is irradiated with the X-ray beam. And the another material, so we had seen that 50-50 sample was the best for this. So we tried another composite, and that is the PMMA. We add a polymetacrylate, okay? And when we add a PMMA to my bismuth iodide, okay, and studied it, so what we had seen is, as I am increasing the concentration of PMMA from 40 to 70%, again the crystallinity of my composite is being decreased. Okay, you can see PMMA 70 is showing almost a amorphous nature. These two peaks, which corresponds to almost the 15 degree and 21 degree, they corresponds to the peaks of PMMA. Okay, so they has been seen with the higher counts. You can see in the PMMA 70, but it ensures that BI3, since I am getting all peaks corresponding to BI3 in these samples, that means there is a tendency of BI3 being embedded even in the polymer matrix of PMMA. And through the SEM and EDEX, we could able to get this analysis that how the sheets of PMMA are rolled. Like we are getting the planar sheets, and they are rolling. They are being rolled at the edges, and these BI3 particles are embedded at the edges. So what we had seen through the addition of PMMA is that band gap of this composite is found to be 2.44 electron volt, which is a band gap which is lying between the band gap of PMMA and bismuth iodide separately. The band gap of PMMA is around 4 volt and BI3 is around 2 volt. So we got something like 2.4 volt, which I have got through the UV visible spectrometry. And this 2.4 electron volt is a desired band gap, I should say, for a X-ray detector material. Okay, and also we had seen that we got a like in case of a PS, when we added a polystyrene or some, we had seen that we got a single phase, hexagonal phase. Now we got the mixed phase in our samples. Okay, so so what our samples show well-balanced properties of both BI3 and PMMA, ensuring better charge collection efficiency for wider range of voltages. You can see the switching curves. These are the switching curves which we have drawn for PMMA. Okay, so the top shows my photo peak current density versus the bias voltage. So we have seen that the photo current is increasing as I'm increasing the voltage, and also the this has been done for two dose rates, for 30 kilovolt and 60 kilovolt. Corresponding to 30, we have a dose rate of about 1.68 milligray per second per centimeter cube, and for the 60 kilovolt, we got a dose rate of around 5.33 milligray per second per centimeter cube. So these are the, so we had seen that on increasing the voltage, my photocurrent density is increased. So if I sum up my results of the PMMA, what I got is for an ideal X-ray detector, high photocurrent and low leakage current are the key parameters. In PMMA series, PMMA 50 is considered as a optimal sample because of better SNR through, though having low photocurrent, but low leakage current too. That is why, though the photocurrent is low for the PMMA 50, as we had seen for the PS 50 also, but since the SNR is high, low photocurrent and also the low dark current, so SNR remain high. Okay, so even for the PMMA series, PMMA 50 was considered as a optimal sample to study. And when I compare it with the PS 50 sample, so of course PS 50, whose a high SNR value, and we had seen that the SNR value comes out to be very high, and it showed a low NED, that is noise equivalent dose rate, and which is desirable because lower the noise equivalent dose rate, higher would be the contrast image, which is the requirement for PET analysis, for MRI. Okay, though it is not a good thing for CT, but for PET and for MRI, the material which is being used for making the films should have a high contrast imaging. Now what happens is, as we were just listening to Professor Kerr, the amount of filler is very important if I want to see what is the effect of filler being on my polymer composite. So what we had chosen this filler as both, like we had chosen many fillers, but here I am just reporting the one. We had choose multi-walled CNT. Okay, and we have added it in a very, very small proportion. We tried all small from 0.01 to 0.05, and we had seen that with the addition of this MWCNT, multi-wall CNT, my photocurrent has been increased enormously. Okay, you can see the photocurrent of my S3 sample, which corresponds to the addition of the filler. It is quite less than we can work on. We are still working on this, that how to increase the photocurrent, but the trade-off is that even the dark current is being increased. Okay, and we have to work out on it, so that work out on the synthesis process, work out on the electronic properties, so that what shall we do to decrease this leakage current. So this work is still going on, and we are working on it. So what idea through the literature only we come to know that the conductive fillers such as multi-wall CNTs or single wall CNTs, they are effective in enhancing the conductivity of the polymer based composite. So what we had seen that through the EDEX or through the SEM analysis, we had seen on addition of conducting fillers, these dispersed conductive particles, they start creating clusters leading to percolated network. And these interconnected network of MWCNT facilitates conduction across the composite material. That is how the photocurrent has been increased by 2 order, but SNR remain low. So still this is a question, we are working on it. So how to decrease the dark current to have the BET. But we are sure that the addition of conductive fillers can solve the problem of high resolution, low energy needed for creating direct detectors, for designing direct detectors. Now, this is the state of art which is being presently used in medical industry. This is the amorphous selenium photoconductors. This is scintillator based. Okay, and these are the limitations they are talking about at the present. So though the work is preliminary, but we have reached to almost the same idea. Even we are getting the similar resolutions, and the bias voltage which we are here, it is 10 volt. That means 10,000 volt per millimeter, which is quite high. what we have obtained, our result is at very low bias voltages, that is lying between 1 to 20 volts, which is very, very less. So we are hopeful that we are going to work on it and improve the characteristics. So what is, so this is on, we are working on. And before I before I throw the audience for questions, thing is, what is the recent and where people are being researched is that in medical field, digital X-ray is a new thing. Okay, this is a mainstream which is replacing the conventional film-based detectors. Okay, and also the dual energy imaging is being coming into few of the hospitals abroad. What is the dual energy imaging? Where the image capturing like your detector is capturing both the low energy X-ray and high energy X-rays at one simultaneously. Okay, so the contrast which is going to show on a film would be high, and also the flat people are working on a flat panel CT scanner devices, so that the spatial resolution and both the temporal resolution of a detector is high. So spatial resolution we all understand is because of the FWHM has to be low for getting a good spatial resolution. We can add pixels, like we can build tiles of these detectors and connect them in such a order that we get a high resolution. Temporal is being used, which is dynamic in nature. That means we are providing number of frames per minute or per second. So how many frames a device can produce. So the temporal resolutions and the spatial resolutions we are all the research fraternity is working on. So this is the work I wanted to share with you people. So if I want to conclude my talk, I can say that the polymer composite provides a low cost, stable, non-toxic composite detector with high signal to noise ratio, improved crystallinity, and consistent response to soft X-rays over several cycles without a degradation. And these X-rays, polymer metal iodide composites, they are not degraded by the moisture, though the Bi3 is sensitive to the moisture content, but its blending with the polymer results into a stable polymer composite showing high signal to noise ratio. Thank you very much.
Thank you, madam, for this very well talk. And now session is open for questioning. Any question, please? Anyone?
So polymer is your field also, Verma sir. So you may ask if you have any queries.
That polymer is insulating polymer or electronic conducting polymer, is this?
Yes.
PAPM. And
that
BI3 is
it's a semiconductor.
Semiconductor.
Yeah, it's a semiconductor. That is why we use them as a conductive particles.
Okay.
Yeah. And this we had seen through the SEM analysis. They are well dispersed, and we are actually trying to build a nano composite of it. So by irradiating with the beam, so that even if there are microclusters at the junction of the network, they might break into nanoparticles, and that may enhance the detector property of a direct detector. So
if you permit, I will try to check this behavior by using DFT also, because I have gone through this polymer structure as well as this BI3. It's a really interesting material. So if you permit, I will work with the DFT on this material.
Yes. Yes, of course.
I will contact you.
Collaboration is always open,
Yes, yes,
and
yes.
under NEP, I think more such collaboration should come.
Okay, okay.
This is
So I
what
will
the
contact you.
intention of the new education policy is.
Yes, yes.
Right, and this is all about collaboration because we are jointly and organizing this seminar. So we are just working on the lines of guidelines of NEP. So it was a nice lecture, Garg ma'am. And actually, I had just one question, that if you are using polymer and you are exposing it to X-rays, then there are several kinds of reactions may take place, and it can also break the bonds of polymers. So you have to optimize the energy of the
Yeah,
X-rays.
we need to.
Yes.
That is why we are working on the soft energy range below 50 kilo electron volt.
Right,
We are
right.
working in the, because even if we go to the higher range of mega electron volt, then the penetration would be high, and then it might degrade the material. So we really have to optimize our X-ray energy of the X-ray to get a maximum charge collection.
Right. Yeah. Right. That's true. So thank you so much for this very interesting lecture.
Okay, thank you so much.
Over to Verma sir.
Okay, thank you, ma'am. And now this is time for oral presentation, and we have 15 oral papers here, 14, and 10 minutes, 10 minutes each allotted to every speaker. So I think speakers should be ready. And 8 minutes will be given for the presentation and 2 minutes for general questioning. Because for best oral presentation, the evaluation process will be there on the basis of innovation of work, presentation skill, and the depth of understanding, question answers, and the time management. So the time management is very important. So please, you have to complete your presentation within 8 minutes, and 2 minutes will be for discussion session or questioning session. So please be ready. And the first presentation as per the list is OT1, that is from Manojit Day, LA doped co-ferrite synthesis structure and vibrational study.
Sir, I would like to interrupt just for 1 minute because participant may not be aware that they are being judged, and we have 2 judges. So please, I may introduce to the participant. You will be judged by the chairperson himself, and along with him we have another judge who is Dr. Vinod Jena from Chemistry Department of Government Science College, and they have a judgment sheet. I think they have it, and they will judge on certain parameters. So, sir, you may discuss the parameters of judgment if you want. Okay.
So, Manojit Day, are you ready? Now.
Yes, sir. Yes, sir. Yes, sir.
Share your screen and start your presentation.
Sir, I'm here. Yeah. Am I? Okay. Sure, sure.
Your screen.
Sir, I think my screen is visible to everyone.
Yeah, it's visible.
Hello. Okay, okay. Am I audible also?
Yes.
Okay. Okay, sir. Thank you. First of all, thank you very much for organizer for giving for the opportunity for presenting one of our ongoing project work, that is the lanthanum doped cobalt ferrite synthesis, structural and vibrational study. I am Dr. Manojit De from Choksey Group of College. Right now I am working as an assistant professor here, and I did my PhD from Guru Ghasidas Vishwavidyalaya. It is in Chhattisgarh. Now, coming to this summary or sketchy summary for this presentation, that is the first of we will discuss about some basic of the spinal structure, then experimental details, result discussion, conclusion, future aspects, and the diagnostic. Coming to the spinal structure, this is the general formula for the spinal structure, the AB2O4, where A and B are the tetrahedral as well as octahedral side, and O is the oxygen side. Now, here in a 1 cubic cell of the spinal structure, there are 64 tetrahedral site and 32 octahedral sites are there, and there are metals and as well as oxides are contained. According to the distribution of these cations, that is A and B cations, we can classify the different type of the spinal material, like that normal spinal, inverse spinal, lacinic spinal, and the distribution is like this. If we are talking about the spinal ferrite, that B side it is generally for the normal spinal atom, normal spinal structure, that Fe3 it is in the B side only, and for the inverse spinal, this Fe3 it is distributed over the first A side as well as B side both. And the example for that normal spinal structure is that is a zinc ferrite and the nickel ferrite, cadmium ferrite, manganese ferrite, magnesium ferrite, cobalt ferrite, all are the type of the inverse spinal structure. Now, why this spinal type of material are very much important? Because a huge number of applications that can be done by using the spinal structure. As we synthesize the material and strategy, which type we want to monitor or we want to work on, then we can find the different type of enormous type of application for this spinal type of material, like the supercapacitor, the metal ion batteries, water splitting, as well as different. Very recently, it is very much important that different as well as biomedical application for this spinal structure also very much interesting nowadays. Now, coming to the objective of this present work, we just synthesize the cobalt ferrite as well as the lanthanum to cobalt ferrite. For this, actually main focus is how that magnetic property of this type of material or cobalt ferrite has been monitored, has been changed by using of the lanthanum doping. That is the main. But in this, this is on one of our ongoing projects right now. And here right now we just in this presentation it is covered in the structural by using the different XRD pattern, XRD studies, and then gravitational study as well as surface morphology studies are there. Now coming to the synthesis method, there are different types of synthesis methods present to synthesize this cobalt ferrite as well as planning with different types of spinal ferrite, like solid state ceramic method, salt gel method, combustion method, Pechiney's method, and every method has some merits as well as demerits. As per our availability, we use the combustion method here. This is the detailed workflow chart for this combustion method. First, we take the precursor material, basically the nitrate solution of the precursor. Every metal ion will be took that time, and they are mixing by composition, and then on a hot plate they are mixing here, and after that it's self burning process is there. There are some fuel also, we are adding glycine was there, and after that combustion takes place. Then we just take the we just take that material in a mortar and pestle, and we just take it in the fine powder, and then calcine. After calcine, we can take the phase analysis by exactly how that phase is. If there are some other phases are there, we just do the again sintering process. Then after that, we go to the mixing and making the pellet, and then sintering process. After that, the material is ready for the characterization, and different physical characterization like that structural characterization, morphological and elemental analysis, as well as vibrational analysis is done for this material here. Now coming to the XRD pattern, this is the XRD pattern for the doped lanthanum material, cobalt ferrite material. This is the pure lanthanum. This is 5%, 10%, and 15% dope of lanthanum doping. As there is no such extra peak, except this around 15% doping, there is a small peak of that lanthanum ferrite also. Just powder phase identification is done actually by the high score and software connected to the ICD2 PDF4 that database, and all the sample also are well matched. The peaks are well matched for the GCP based data for the cobalt ferrite. The shifting of that here, this the major peak, that is 311 peak, which is shown here, the short range position, and how this peak is getting shifted as the lanthanum is doped here. This is because of the a mismatch of the ionic radii of the doping material as well as the host material. Now coming to the different analysis from the PEXA-RD, first we calculate the lattice parameter for the synthesized material. As we see here that lattice parameter will increase with the, as you increase the doping of the lanthanum concentration as well as crystalline size by calculated by the device Scherrer formulas, and it is continuously decreasing, and as well as some jump length as we are looking about that magnetic ions and the magnetic property. The jump length in the octahedral side as well as tetrahedral side is by calculating by this formula, and we just plot this the same type of nature is found there for the octahedral side as well as tetrahedral side. Now, if we dope some foreign material on a host material, then there must be some strain produced in itself. Like strain, we just calculated by the induction formula and plotted this graph and fitted with the straight line, and then we can calculate the strain from that equation. Now, if we plot that as we see here, that strain is continuously increasing with the lanthanum content as well as slope is decreasing and increasing. That's why in this table it is also noted that strain in here, and different parameters like the lattice parameter, crystalline size, X-ray density, and the jump length in the octahedral and tetrahedral side, and unit volume are calculated from using different formulas, and it is noted in this table only. Now coming to the morphological, for every material we can see there is a fluffy type of nature, and the porous type of nature is there, and this is one of the characteristics. We can say any type of spinal ferrite material, and if we see this insert figure, it is the index of that material, and there is no such extra peak for the we can find that, so and include that contamination. For coming to the Raman this is the vibrations of the metal ions with respect to the different anions, that is oxygen here. This is the basic from the book theoretical analysis we can calculate that. There are 5 different Raman active modes are there, and as we see here that A1G, this is the symmetric stretching of the oxygen anions, and EG, this is the symmetric bonding, and we can find the structure also by using of this Raman spectroscopy technique. That here that A1G, this is
last 1 minute, please conclude.
Inverse. Yes, sir. That is it is the shoulder peak is there. That is the main signature peak for the spinal ferrite. Now coming to the conclusion, we just synthesize lanthanum and the cobalt ferrite. It is by combustion technique, and XRD pattern we just calculate every parameter, and same pattern is the porous type of nature is found, and the Raman spectra, this is a conclude also the spinal structure, and there are different feature aspects where we can say that different application of the spinal ferrite is available here, and there are a few publications of there, and I acknowledge my supervisor Dr. H.S. Tiwari sir and UGC for their granting me the PhD fellowship, and I would thank all of my collaborators as well as papers, co-authors of the paper. No, thank you for your kind attention.
Okay, so one question can be permitted because time is already 10 minutes. Any question? Okay, Mr. Day, thank you. Next presentation is on structure, optical, morphological, and
plot. We have got the band gap of the prepared sample. From the theoretical analysis using quantum espresso, we have calculated the band structure and band gap from the quantum espresso code. Finally, optical and theoretical band gap has been compared. Morphological analysis. This is the STEM image of my synthesized CDT nanocrystal, and this picture is the average particle size calculated from the TEM image. From the TEM image, it is clear that hexagonal shaped CDT nanoparticle has been prepared. And this is the histogram. From the histogram calculated from TEM image, we have find the average particle size about 7 nanometer. Structural analysis. This is the XRD of the CDT nanocrystal, and we have done the Rydberg refinement of our XRD, and from the peak we can conclude that the prepared CDT nanocrystal have hexagonal in phase, and after Rydberg refinement we find this we find the parameters like unit background parameters, peak shape parameters, and shape, phase, fraction, etc. Finally, obtained parameters from the Rydberg refinement we have further used in the DFT calculation. Optical properties analysis. This is the absorption spectra, and this is the Tox plot. From the Tox plot, we have calculated the band gap of the CDT nanocrystal as 2.4 electron volt. And this is the theoretical band gap calculation. This is the using Rydberg refinement data of the prepared hexagonal CDT nanocrystal. We have taken out different lattice parameters, and those parameters have been used for the further DFT plus U calculations. Band structure have been shown in the figure. This is the band structure of the CDT nanocrystals, and from the band structure we have been calculate that the band gap of the CDT nanocrystal is about 2.1 electron volt, which is further matched with the calculated band gap of the calculated optical band gap. So our optical band gap was 2.4 electron volt, and from the theory we get the band gap of the CDT nanocrystal is about 2.1. So we can conclude that both calculated band gap and the theoretical band gap are approximately same. Conclusions. In this study, hexagonal CDT nanoparticles with hexagonal phase have been prepared through weight chemical methods. TEM analysis and XRD peak profile analysis confirms the hexagonal phase of the nanoparticles. Particle size has been obtained as about 7 nanometer from the TEM analysis. UV visible spectroscopy has been used for the optical band gap and obtained value of the band gap as 2.4 electron volt. DFT theory has been employed for the determination of band structure of the prepared hexagonal CDT nanoparticle, where the refinement parameter from Rydberg are used as input data. Finally, the optical band gap calculated from Tox plot is nearly matched with the theoretically calculated band gap of the semiconductor nanoparticles. These are some references. Thank you.
Okay, now session is open for questioning. Question from audience first. No one. So Sangeeta, I have some questions. Can you hear me?
Yes, sir.
So you have performed DFT also by using quantum expression, and you have used DFT plus U, that
Yes, sir.
forward correction. So what is the value of U you have taken for your calculation for this material?
Yes, sir. Yeah.
That the value of U you have taken, what is that? And how you have decided to take that particular value U? You have the data?
Yes, sir.
Give the value of U. Your voice is not coming to me. No sound. Olivia, Anta, I think there is some network issue outside. Okay, now time is over, Sangeeta. Thank you. Next speaker. OT5. Amino acid derived smart ABC BA type anti-fouling biohybrid. Who is going to present this? Devendra Kumar, SK Arif Muhammad, Anand Kumar, and Sanjeev Banerjee. These are the authors of this paper. Who is the speaker of this paper? OT5. No one. In comments box, please give your presence. You know your oral presentation number. So who is going to present, you have to give the response. So we should proceed to next one, OT6. Dharamveer, Pawan Kumar, Desraj Singh, Devendra Kumar, Ram S. Katyar. Who is going to present this paper?
At least if you are not going to present, then say that you're not presenting, yeah, so that we can go further.
I think no one is present here for the paper also. What's about OT7? The students from the research group, CM Nandan War, NK Kokode, AY, and weight chemical synthesis and luminescence properties of PB3BiPO4 SN3 positive phosphors. So what to do now?
So list exhausted, everyone presented actually. Do we have any? Okay.
28, Nisa, Pawan Kumar.
Sir, somebody is talking. Chandra Hasya Nandan. कुछ है ऐसा. Somebody is want to speak.
So just a minute, we are going to present.
Sir, yes, sir. Presenter is there.
Which number?
Toble sir's group.
Oh, okay, yeah, good one. CM Nandan. Okay, OT7. You're ready, Mr. Nandanwar?
Yes, sir. Yes, sir.
Okay, so now it's
नाही आता स्क्रीन नको शेअर करू पहिले तर करूया
share your screen and
चालेल चालेल
start your presentation.
ते करू शेअर करतो आय एम शेअरिंग सर आय एम शेअरिंग
Yeah, share your screen.
सर विजिबल
No, not so far.
सर इट इज विजिबल
No.
आता तिथं तिथं 1 minute सर आता त्याच्यावर ना हे मिनिमाइज कर तिथं ना
Still not visible.
हां आता विचार सर इट इज विजिबल
No.
कर दे इथंच शेअर आता झालं सर इट इज विजिबल स्क्रीन
Yeah, now it is visible.
So, good afternoon to all our organizer and participant. Myself, Chandrasya Motilal Natanwar, research scholar from CHLR, NH College, Brahmapure. I am presenting oral on wet chemical synthesis and luminescence property of trivalent samarium to PB3BiPO4 3 phosphor for near ultraviolet base solid state lightning. There are contents, introductions, synthesis, characterizations, result and conclusions. First of all, the introduction. What is luminescence? In fact, the phenomena of cold emission of light is known as luminescence. Luminescence process involve at least 3 steps. Energy observed causing electronic excitation, storage of absorbed energy, emission of photon depending on the storage time. Some types of luminescence and there of the list: photoluminescence, cathodoluminescence, radioluminescence, electroluminescence, chemicoluminescence, bioluminescence, triboluminescence, mechanoluminescence, and thermoluminescence. Introduction to the phosphor. Rare earth dope orthophosphate phosphor has considerable high thermal and physical stability. Their excellent stability make them more suitable for high power LEDs and outdoor lighting markets. Luminescence material doped with trivalent samarium doped have drawn much interest for its white emission. There are wet chemical synthesis of a samarium dope PB3BiPO4 phosphor. Powder sample of the PB3BiPO4 SM3 was synthesized by the wet chemical synthesis, and the starting materials are lead nitrate, bismuth nitrate, ammonium dihydrogen phosphate, and samarium oxide. The mixed all starting compound and kept stirring for 1 hour on a magnetic stirrer to get a uniform transparent solution. The result of transparent solution obtained was kept for drying in an oven maintained at 100 degrees Celsius for 10 hours, and after which is powder from was obtained, and then the PL characterizations of the room temperatures. Characterization of the PB3 BiPO4 samarium 3 phosphor of a photoluminescence behavior. It is the result and discussions. It is excitation spectrum of PB3 BiPO4 3 samarium 3 phosphor. The excitation bands of the spectrum
Your voice dropped.
the intensity of 404 nanometer is the highest is the excitation spectra. The emission spectra of PB3Bi, PO43, samarium 3 plus phosphor. Photoluminescence emission spectra of PB3 Bi PO43 samarium 3 plus when excited at 404 nanometers under the strongest peak of 599 nanometer contribute to the orange emissions of SM3 and due to the 4G 5/2 5/2 6H7/2 electric dipole transition. The emissions observed at 563 nanometer is mainly from 4G 5/2 to 6H5/2 magnetic dipole transitions of SM3 ions. SM3 ions concentration in the PB3Bi PO43 phosphors of samarium 3 plus dope PB3Bi PO43 phosphor having a varying concentrations 0.3 mole percent to 1.5 mole percent was prepared by the wet chemical synthesis. The maximum of the emission intensity is observed at 1 mole percent of samarium 3 plus ion due to concentration quenchings. Then conclusions. In the presented work of trivalent samarium doped PB3Bi PO43 phosphor was prepared by the wet chemical synthesis. Emission spectra show the characteristics band of trivalent samarium doped ions observed at 563 nanometer is a yellow color and 599 nanometers of due to the orange color. The concentration quenching is observed at 1 mole percent. The PL result show the excitation peak of 404 nanometers, which is away from excitation, and it is useful for the solid state lighting in the lamp interested. Possible application. There are the digital clock, battery level indicator, traffic signals, street lights, residential outdoor area, information boards, buildings, etc. etc. Thank you, sir. Thank you. Thank you, sir.
Okay. Now open for questioning. Any questions? No question from audience. Anyone, please? So I have a simple question. Why you have taken this chemical method for the preparation of your material? Hello?
Sir,
What is the reason behind this
sir,
method? Yeah.
wait, first of all, uh, first time is the wet chemical synthesis of the Pb3BiPO4 of the samarium 2.
Okay. Why you have chosen this material, this method? Is there any other method to prepare such materials?
Solid state combustion, soul gel method.
So many methods are there, and you have taken this. Why so?
Sir, wet chemical method of easy and low temperature method.
Okay. Good one.
Thank you, sir.
Next, who is present? Okay. Nisha Pawan Kumar, Prasanjit Sarkar, Ram S. Katiyar. Impact of S upon SN ratio on physical properties of orthorhombic alpha-10 monosulfide thin film.
Hello, excuse me, sir.
Anyone present here? Yes, Dharamveer Pawar.
Yeah. Yes, sir.
Which number? Which number? Dharamveer Pawar.
6. 46.
Achha, 46. Okay, okay. Yes, Dharamveer Pawar. Okay, so share your screen and you will be given 10 minutes to present your work. Okay, Dharamveer, start. The screen is visible, okay.
Visible, okay. Thank you, sir.
The screen is visible.
I am. Yeah.
Yeah, sound is also.
Screen share here.
Yeah, same.
Visible or not? Okay, okay. Thank you, sir. Good evening, everyone. My name is Dharamveer. I am a research scholar, Department of Physics, Gurul Kangri Deemed University, Haridwar. My research topic is a synthetic approach to achieving high conductivity and thermal analysis of NH2Q4 2H2O with ZrO2 composite electrodes. First one, the details of my research is, in this research work, we use two types of compound NH2Q4 2H2O and ZrO2 synthesized by chemical route method with a molar ratio, and we prepared these material and done characterized by XRD, FSM, EDX, FTR, TJ, and conductivity measurement. The main objective of my research work include in this work is to study of conductivity and thermal stability based these materials. First one, introduction is fuel cell. In modern society, there is a huge demand for emerging ecology and a renewable energy source. Fuel cells are becoming an attractive renewable energy generation source. New studies are based on the high conductivity and good mechanical properties of solid acid electrolyte for fuel cell. Solid electrolyte exhibited high ionic conductivity and good mechanical property for solid state batteries, fuel cells, sensors, memory cells, etc. Solid state fuel cell operate at intermediate temperature, which generates for other fuel cell technology, in which solid acid phosphate has attracted the attention of researchers because it used in intermediate operating temperature. In this group, CDP is a widely used solid acid, but we use here NaH2 PO4 2H2O, SDP 2H2O, a solid acid that exhibits high proton conductivity in its superprotonic phase, which increase the conductivity many orders of magnitude. Phosphates fundamental research technology with nano material attracting attention. The presence of in this work ZRO2 improving the conductivity and stability of this material. This work is devoted a study of composites SDP2H2O, 2H2O with ZRO2 for intermediate temperature application. It is considerable for scientific and practical interest for find a heterogeneous additive capable of increasing the proton conductivity. ZRO2 basically is a particular oxide due to its ability to absorb and retain water temperature due to the effect of mechanical stability. Experimental section. In this section, we used these materials NaH2O, 2H2O and ZRO2, and we synthesized by the chemical route method with mechanical milling by an agent mortar at the molar percentage ratio. After that, we based on pellets make pellets of powder of these samples, and electrode were attached on both sides by silver paste by a vacuum coating unit. First one, result and discussion. XRD, the phase transition in the range of 2 theta 20 to 60 of SDP 2H2 and ZRO2 and their composites analyzed by XRD. The monoclinic phase space group P21C for SDP 2H2 and ZRO2 powder also monoclinic phase at below the transition temperature. In the XRD, CS2 NH2PO4 O7 CSPO4 respectively, intensity peaks was found to decrease with increasing the heterogeneous additive concentration of ZRO2. ZRO2 have a monoclinic phase at room temperature, which is given already. Second point. The intensity of the peak decreased by changing concentration of ZRO2 with SDP2H2, which suggests an increase in the degree of atomicity in the composites. This phenomena leads to ion diffusivity with ionic conductivity and stability. The XRD patterns confirm the crystalline structure of SDP2H2 and ZRO2 and their composites. Next one is Epicen EDX. Epicen EDX show the surface morphology investigation and identify the chemical composition of the material. The pure HDP2S2 and ZrO2 phase appeared as porous powder-like crystalline networks, whereas the crystalline group of phosphate appearing to climbing to ZrO2 inclusion and binders. A dense layer of phosphate left cell. The octane of HDP2S2 material was composed of particles that are heterogeneous between HDP2S2 and ZrO2. HDP2S2 and ZrO2 according to the complex analysis of TGA, DTA, and EDX, which is by the change in XRD pattern. ZrO2 form effective chemical interaction with HDP2S2 which support high proton path in the conductivity. In the recorded in the range of 400 to 4000 centimeter inverse. The spectra of HDP2 and when ZrO2 added with HDP2, it did not produce any obvious change in the pattern of absorption band in FDR spectrum. The conductivity increased in a lower temperature by motion of PO4 tetrahedral, which seen in IR spectrum. Although this indicates a slight increase in the band frequency of POs, which show an increase in conductivity. Density of the composite was observed with the ZrO2 increase of the XRD results. The IR spectra of the composite provided significant change in chemical composition, functionalization, and other change. Next one is TGA and DTA. The residual water Excuse me, sir. Hello.
Yes. Continue.
Okay. Thank you, sir. The residual water content in the powder was studied by TGA DTA analysis, which shown in figure. The main weight loss of powder investigated by 10 degree per minute under an air atmosphere up to 500 degrees Celsius. The total weight loss of HDP2S2 and ZrO2 given in this. The total weight loss for composites HDP2S2 is less as compared with pure HDP2S2, which show a weight loss decrease at the value of ZrO2 increase. The conductivity is directly affected by the dehydration of HDP2S2 and their composites. TGA DTA saw a slowdown in composition on adding ZrO2 and results indicate an improvement in thermal stability and conductivity. This effect endothermic with the superconducting phase transition will support the conductivity measurement. The TGA DTA result for the composites indicates and
please conclude now.
Okay. The most important part of this research is temperature dependence conductivity. HDP2S2 conductivity increased by 3 orders of magnitude because of the pure interaction between the solid state and ZrO2 increase the stability of composites. HDP2S2 with low ZrO2 additive was found to be in good agreement with ionic conductivity and stability. These composites show a strong ionic conductivity and thermal stability, which make them appealing for application in a variety of chemical devices and fuel cells. Our results upon a new possibility for SDP, CDP, and this type of compounds and other solid acid that are attractive for using phosphoric acid fuel cell. Conclusion is ZrO2 with SDP2S2 composite show saving, cost reduction, and improve conductivity, and which making them attractive in intermediate temperature fuel cell. The mechanism of proton transport within these materials confirmed by FDR, TGA, DTA, so supersonic conduction confirmed by Nyquist plots, and are result in proton conductivity observed both low and high temperature range increases, and the successful use of this material a confirmation urgent feasibility of its as a proton conductive electronic in real application. My research, published research papers, I have published 9 research papers in different journals. I heartily thankful to Gurukul Kangri Deemed to University for providing facility my research work, my thesis work in the material sciences lab. Okay, thank you.
Okay, one question can be allowed. Any question?
Yes.
Any question from audience, please?
Anyone, sir? Question, anyone?
So, Mr. Dharamveer, I have very small question for you. So this composite material is some sort of liquid solid type composite material.
Solid.
Solid.
We use solid.
There is no two-phase type thing, single phase composite material.
Yeah.
Conductivity that is in the order of 10 to minus 3.
10 to minus 3.
10 to
If we
minus
use CDP, actually CDP is the most highest conductivity material in this group. But if we add any oxides like ZrO2, Al2O3, Di2, and mix salts, then we increase the conductivity. And if we use in confined this experiment in confined conditions like any container without air, then we increase also conductivity.
Okay. Good one. Thank you.
Okay, thank you, sir. Thank you.
So next speaker who is present now. Nisha Pawan Kumar, 48. $49. AP Pawar. Fuel cell, yeah, it's a. Anyone? OT 10, 11. Please give response.
Count. Hello, sir.
Yeah.
Myself, Atul Erpode.
Okay, so your paper number is?
My paper number is, sir. Wait a minute, I will check.
What is the title of your paper?
My paper title of my paper is Synthesis and Luminescence Properties of K3
Okay, OT10. Okay,
50.
Are you ready?
Yes, sir. I am ready.
Okay, now share your screen and start your presentation. So it's,
Okay, sir. Wait a minute.
3:57 already here. Start, please.
1 minute, sir. Whether my screen is visible, sir?
Not yet.
Now is it visible, sir?
Yes.
Thank you, sir. Good morning to all organizer and Good evening to all organizers and participants. Myself, Atul N. Yerpude. I am from Department of Physics, Nevzabad Hitkarni College, Brahmapuri. I am going to present the topic synthesis and luminescence properties of K3La of orthophosphate, which is doped with trivalent europium phosphor for near UV based white LED applications. Contents are introduction, synthesis, characterization, results, and conclusion. Luminescence is nothing but emission of light which is in excess of that attributable to black body radiation and persists considerably longer than the period of optical radiation. And some of the luminescence types are given below. I'm going to skip that. And synthesis method, what I used is wet chemical, which is given here in the slide, in which I considered starting material as a potassium nitrate, lanthanum nitrate, ammonium dihydrogen orthophosphate, and europium oxide. The starting material are taken in proper stoichiometric ratio and dissolved separately in double distilled deionized water. Then mixed all starting compounds and kept for stirring for 1 hour on magnetic stirrer to get uniform transparent solution. The resulting transparent solution was kept for drying in an oven maintained at 100 degrees Celsius for 10 hours, and after that which converted to powder form. Okay. Then we had studied or characterized its PL behavior. Then PL behavior, excitation and emission we studied. In that I'm going to tell the excitation spectrum of the potassium lanthanum orthophosphate, which is doped with trivalent europium phosphor, monitored at 593 nanometer emission keeping constant, and we got excitation bands at 362 nanometer, 376 nanometer, 383 nanometer, and 394 nanometer respectively, and corresponding electronic transitions are given as 7F0 to 5D4, 7F0 to 5G3, then 7F0 to 5G2, and 7F0 to 5L6. And the intensity of 394 nanometer is maximum among the obtained excitation bands. Now, emission spectra. The photoluminescence emission spectra of potassium lanthanum orthophosphate with trivalent europium excited at 394 nanometer, or you can say 394 nanometer kept constant. Then the strongest peak obtained at 593 nanometer contributes to the orange emission of EU3 plus ion due to the transition 5D0 to 7F1 magnetic dipole transition. The emission observed at 615 nanometer is mainly from the D50 7F2 electric dipole transition of EU3 plus ion, which is in the red range. Now, EU3 concentration in potassium lanthanum orthophosphate, EU3 doped phosphor varying concentration from 0 to 1 mole percent was prepared. The maximum emission intensity is observed at 0.3 mole percent of europium ion. Okay, sir. And then in the present work, potassium lanthanum orthophosphate, which is doped with trivalent europium phosphor, was prepared by wet chemical synthesis. Emission spectra shows characteristics bands of EU3 plus ions observed at 593 nanometer and 615 nanometer, which are orange and red in color respectively. The concentration pinching is observed at 0.3 mole percent. The photoluminescence result shows excitation peak of 394 nanometer, which is away from excitation and is useful for solid state lightning in the lamp industry, and some of the applications for this material are given below. Thank you, sir. Thank you very much, sir.
Okay. Now session is open.
Yes, sir. I have one question actually, because it is related to luminescence. And you claim that you have developed this phosphor for white LED. So can you explain?
Because, madam, in many white LEDs, there is a color rendering problem, right? So this phosphor contains emission in the range of orange and red. So it is useful for white LEDs because it reduces color rendering problem.
And what is the role of lanthanum in this compound?
A role in the sense, ma'am,
Does it
exactly I
contribute to
didn't get the question.
luminescence? Does it enhance the luminescence or color rendering? What is the role actually?
It enhances the luminescence, ma'am.
Okay, thank you. That's all.
Thank you. Thank you.
Any other question? No. So I have a very fundamental question. You have everyone is using that material in mole percent. So fundamental question is, what is the difference between gram percent and mole percent?
Mole percent.
You have taken
Gram
that
percent, difference between gram percent and mole percent.
3 mole percent of this. So how much amount of this EU3 positive materials you have taken in this particular work?
Calculation. I didn't had a calculation with me now, sir. So if I had, then I can able to do.
Okay. Okay, thank you.
Thank you, sir.
Next speaker, IT 11.
Sir, OT9. I am ready with my presentation. OT9.
OT9 is present. Okay. So, fuel cell, promising alternative energy source with less pollution.
Yes, sir. Yes, sir.
Okay. Now share your screen and start presentation. Welcome.
Okay, thank you very much, sir. Is it visible? Is my presentation is visible?
Yes, it is there.
Yes, it's visible. Sound is okay.
Okay, thank you, sir. Good evening to all the participants and organizers. Myself, DM Parsuramkar from Department of Physics, NS College, Brahmapuri, and I am with my colleagues AJ Mungole and AP Pawar from the same college. My today's topic is a fuel cell, which is a promising alternative energy source with less pollution, less greenhouse gas emission, and high efficiency. In that context, first of all, we have to know what is exactly the fuel cell is, or how this fuel cell is working. What is exactly the fuel cell is? Then fuel cell is an electrochemical device that directly converts chemical energy from a reaction between a fuel and accident into a electrical energy. And oftenly they are offer a clean pollution-free technology to generate electricity, which is electrochemically at very high efficiencies. the basic principle of this fuel cell, means how the fuel cell is working. What is the basic principle behind the working of fuel cell? The basic elements of this typical fuel cell consist of one electrolyte with one porous anode, which is negative electrode, and second porous cathode, which is positively electrode. In this fuel cell, the fuel and oxidant gases flow along the surface of the anode and cathode respectively, and they after react electrochemically in three-phase boundary region established at the gas, electrolyte and electrode interface. This particular fuel cell can be theoretically produce electrical energy for as long as fuel and oxidants are fed to the porous electrode. Okay. For this particular fuel cell, there are certain components of this fuel cell. This fuel cell is made up of anode, cathode, electrolyte, catalyst and interconnect, where anode is the negative electrode, as I earlier told, cathode is the positive electrode, both are porous. Electrolyte is the membrane which is in between anode and cathode, which is rigid, and one catalyst is used to, if the temperature of the reaction is less, then that catalyst is used to increase the rate of reaction, and one interconnect is added to the anode side to overcoming the reducing atmosphere of anode to reach the oxidant or oxidant from the that cathode particularly. Therefore, we are using the interconnect. Okay, what is the exact benefits of this fuel cell? This fuel cell particularly minimizes our reliance on petroleum product for energy, because as we know, these petroleum products are nothing but the fossil fuels, and in the future they will be exhausting. Therefore, we have to search out for the alternative energy source, and in that category, this fuel cell is the important alternative for our energy requirement for different aspects. Secondly, these fuel cells produce the less greenhouse gas emission, because at the output side or at the byproduct in the fuel cell, we got the water as a byproduct. Therefore, there is less gas emission here. This is another, it is a more efficient source of energy. Whenever we are, our reliance on petrol is minimized, and in the fuel cell, there are some degradation problem is less. Therefore, these are the important benefits of our fuel cell construction. Basically, the fuel cells are alkaline fuel cell, phosphoric acid fuel cell, polymer electrolyte membrane fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. There are certain 5 type of fuel cells we are introduced, but this actually the solid oxide fuel cell is have more efficiency than that 4 fuel cells. Therefore, nowadays most focus is on preparation or synthesis of the anode cathode electrolyte material for solid oxide fuel cell. Now, our aim is to know how this SOFC works, or solid oxide fuel cell is working. For the solid oxide fuel cell, we have one anode, which is negative electrode, one cathode, which is a positive electrode, and one electrolyte. Okay, actually, we have to introduce the fuel in the form of hydrogen, methane to the anode, and at the same time, at the cathode, we have to feed some oxidant in the form of air, and it at the oxidant side or at the cathode side, there is a reduction between O2, and we get the O2 negative. That O2 negative ions are exchanging from the electrolyte membrane to the anode side, and it reacts to the fuel that is in the form of H2, and then H2 plus O2 negative produce H2O plus 2 electron. Means we have to generate the electricity from electrochemical reaction in between anode cathode interface in between the electrolyte. Now actually we are working on anode material for this solid oxide fuel cell, and for that we have to produce, or we have to synthesize CGO material, anode material, by using combustion method. And because this CGO material are more promising material for the synthesis of anode, because it has less degradation problem, and In the past, there are other certain materials are used to produce the anode, but they have some carbon depositing problem. But this copper material or this CGO material is not having carbon depositing problem. Therefore, we are using CGO as a anode material. For properly, there are 4 composition of copper: 0.4, 0.5, and 0.6%. Okay. The synthesis method is involving a simple combustion method which utilizes urea as a fuel. First of all, we weighing an initial ingredient, then mixing it with the deionized water for 2 hours with constant stirring. Then we have to mix the urea with that component, then mixing and heating for again 4 hours. Then we have to calcinate at 850 degrees Celsius for 3 hours, pelletize that particular material at 4 ton to make the 9 mm of pellet, and then we constantly sintering at 1000 degrees Celsius for 1 hour, and our powder material is formed, which has in your in presentation shows the XRD pattern of that CGO material, which exactly matches with the standard JCPDS file. Now, in the experiment, in the this particular part, we have to measure the lattice parameter also, and we see that A equals to B, and another lattice parameter is C. That means it has the tetragonal structure, or copper, that CGO material, which is made for the anode of SOFC, that is of tetragonal structure. And we see there is a variation in the lattice parameter for 0.4, 0.5, and 0.6 concentration of copper, which is that A parameter is constant for all the concentration, but that C parameters are something changing from for 0.4, and it is almost constant for 0.5 and 0.6 concentration of copper content. Okay, then we have to measure the crystallite size for that synthesized CGO material, and we seen that crystallite size goes on increasing for 0.4, 0.5, and 0.6 concentration of copper oxide, content. Means X content we have to increase, the crystallite size also goes on increasing. Then we have to measure the electrical conductivity by 4 probe method, and the Arrhenius plot for this particular sample is shown in the diagram, and we see there are variation in 0.4, 0.5, and 0.6% of copper content. We see the DC conductivity or DC electrical conductivity for the 3 prepared sample of 0.4 concentration of copper, 0.5 concentration of copper, and 0.6% of copper. So, okay, then we have to measure the sinter density. That is actually the important parameter for making the anode material. How much porous is, because porosity is necessary for the anode material, what amount of porosity it has, and what are the actual hardness of that anode material, and activation energy by using the Arrhenius plot. We have to calculate all those parameters, and in the table we seen that as the X content increases, the density goes on decreasing. Means 0.4% of copper has more density as compared to 0.6%. Then porosity goes on increasing at the copper content is increases. Hardness is decreasing as shown for 0.4, 0.5, and 0.6, and the activation energy again decreases when we increase the copper content in the CGO material. The last conclusion about this particular synthesis is that the first conclusion we have drawn, the XRD for the prepared sample confirm the formation of CGO anode material. Then second conclusion we have drawn, the crystallite size increases with increase in copper content. Means as we increase the copper content from 0.4, 0.5, and 0.6, then crystallite size goes on increasing. Then third one, the conductivity, that is DC electrical conductivity, goes on increasing with increase in copper content up to X 0.6, means from 0.4 to 0.6, the DC conductivity goes on increasing. The hardness goes on decreasing with increase in copper content. Means as we increase the copper content, hardness of that anode material is decreasing, and we found that the highest conductivity with minimum activation energy was found to be for the copper content of 0.6%. Okay, this is all about our the synthesis of fuel cell, which is the very promising, efficient energy alternative for nowadays. Okay, thank you very much.
Okay, thank you. Now open to all. Some questions, please.
Yes, sir. I had a question actually, because earlier during your presentation you said that the electrode should be porous. So did you check porosity of the electrodes you made, the anode you made?
Yeah, it is around 40% porous it has, 40 to 50%.
Okay, so what method did you use to check the porosity?
For porosity, actually, we measure the density first, and we have to minus from, if I just conclude 1 is the maximum density, we have to minus that density. It means it gives us a porosity.
Okay, thank you.
So your conductivity value increases up to 10 to the power 3.
Yeah.
At high temperature.
Yeah, at around 1000 degrees Celsius.
Okay. Okay, thank you. Thank you, sir. Now, next speaker who is ready. This was IT 49. So OT 11. Kanchan Upadhyay. Ronak Kamrakar, Bisen sir. Pritipala ma'am. Anyone? New approach for synthesis of lead oxide and its biomedical application. Presenter is not present. Next, OT 12, Amrita Nayak, SK Patri and B Behra. Effect of substitution of electrical properties of PbTiO3 derivatives. OT 12. Not present. Anyone? OT 13, Sakshi Sharma. Okay, comparative study between novel Jadeno and the buckyball structure and Jadeno hexagonal structure. It's our paper. Where is Sakshi?
Sakshi is not in the meeting actually.
Sakshi is here? No. In the OT 14, Parvati Nayak and SP Patri, study of structure and electrical properties of rare earth modified BIKNB FeO ceramic. Anyone available to present? So what to do now? Should we wait?
Yes, if there is no one to present, then we can conclude this. Bhargavi ma'am?
Hello.
Hello.
Sir, I don't think there is anyone else present.
So I think you should conclude this complete session.
Madam, shall I conclude?
Yes, sure.
Okay. I thank the chairperson of this technical session, Dr. ML Verma sir, for sparing his time out of his busy schedule with this session. I also thank all the participants who presented their research work in this technical session. So I thank one and all once again. And
Judge,
this is
another judge was with us.
sorry, extremely sorry. I also thank Vinod Jena sir, Dr. Vinod Jena is the judge of this technical session. Thank you so much, sir. And a small announcement: we will start the third technical session. That is the technical session of second day. The session will start at 10 a.m. sharp. First is the invited talk that is to be delivered by Professor Ila Raut from DIT Mesra. So please, all of you join on time. And soon after the invited talk, other oral presentations will start. So with this, I think today's sessions are over. Madam?
Yes.
Okay.
Thank you everyone, and please join tomorrow also. We will have very good speakers, and quite interacting sessions will be there. So please join us within time. And thank you Verma sir and Vinod Jena sir.
Thank you very much.
Thank you sir.
Thank you all. Thank you.
Leave कर सकते हैं हम?
Yes. We can leave the meeting now. Bye and have a good day.